Hi everyone, can you hear me? Just let me know if audio, video, everything is fine. Okay, so once you confirm, then we will start. So how are you all? How are you doing? Good morning, everyone. Okay, so now let's get started. So today, in this particular session, we will see PYQs of binary search tree. Okay, so this class is by the way for both Gate CSE and Gate DA because binary search tree, binary tree, these are the this is the syllabus for both Gate CSE and Gate DA. Okay, so let's get started now. Now, I will directly jump to the PYQ, but before that, I will just give you, quick glimpse that what is a binary search tree and how does it look like. Okay. Although I'm expecting here that you know all the things, but just for the quick revision, just for 1 minute revision, let me just quickly tell you. So basically, binary search tree, we also call it BST in short. It is basically some structure which follows some rule. So it is a binary tree only, but it follows one rule. What is that rule? You might already be knowing that let's suppose there is some value here. Let's suppose 5, right? Then on left of this, you can write only lesser than or equal to 5. So which means you can write basically you can have numbers like for example 3 and then you can have 2 here, then you can have 4 here like this, right? I mean 4 must be lesser than 5. So basically all the numbers here must be lesser than 5. And if you're writing 3 here, then all the numbers here must be lesser than 3. All the numbers here must be greater than 3. Okay. Let's suppose you write 7 here, or yeah, you can write 7 here. Then you can also write 6 here because these numbers, all the numbers must be greater than 5. Okay. And then you can write 8 here. So which means that this number 8 should be greater than 7 also. It should be greater than 5 also, right? So that's how basically we have binary search tree. Now, let's just talk about directly PYQs. So before that, let me tell you that I will solve all all means like almost all. Okay, all doesn't mean like if there are like 1 2 PYQs are left, then it might be the case, but all means almost all. Okay, so all PYQs in this session for binary search tree. Okay, so let's get started. Let's see this question, what this question is saying. A binary search tree is generated by inserting in order of the following integers. So basically, suppose we are inserting in this order the number of nodes in the left subtree and the right subtree of the root respectively is. So basically, if you insert in this order, then what you will be getting, that's what they're asking, right? This is an easy question. I think you can solve this, but this question has been asked in GATE 1996. So let me also try to solve this. So basically, here you can say that if we are inserting 50 first, then 50 will be here as a root. Okay. Then you can have 15, which will be on the left of this. 62 will be on the right of this. 5 will be on the left of 15 also. And then 20 will be here. 58 will be somewhere here. 91 will be somewhere here. You have to insert in this order only, right? And then 3 will be lesser than 5, it will be here. And then 8 greater than 5, it will be here. And then 37 greater than 20, it will be here. 60 greater than 58, it will be here. 24 is lesser than 37 and greater than 20. So 24 will be here. So now they are asking number of nodes in the left subtree and the right subtree of the root. So in the left subtree, there are 1, 2, 3, 4, 5, 6, 7, right? So 7, 4 should be the answer. Okay. And here there are 4 nodes. Is this okay, everyone? So by the way, do you have to draw this tree? Do you have to draw this tree? See, you don't have to draw this tree. Why? Because you can just count how many numbers are there which are lesser than 50. Okay. I mean, lesser than 50 in the will be on the left subtree. Okay, of the root. So this is lesser than 50. This is lesser than 50. This is lesser than 50. or maybe how many are greater than 50, anything you can count, right? So, I mean, once you count one number, you will be getting another number. So let me count greater than 50. This is greater than 50, this is greater than 50, this is greater than 50, and this is greater than 50. So you can say these are the four numbers which are greater than 50. So which means on the right side tree, there must be four. Okay. You don't have to draw this tree. Understood? That's very easy. Okay. So B is the correct answer. See, in the answer that is written on the gate overflow, they are saying you can simply count the number by looking at input less than 50. Okay, so they are also saying that you don't have to draw. You can simply count that lesser than 50, how many numbers are there, and greater than 50, how many numbers are there. Okay. Let's now see this. A binary search tree is used to locate the number 43. Which of the following probe sequences are possible and which are not? So this is a good question. Okay. So they're saying that there is a binary search tree, right? I mean, you don't know about the binary search tree, but the tree is used to locate the number 43. Okay. And then you whenever you are searching for 43, then you basically might encounter some of the numbers in between. Okay. Now they are saying that which of the following probe sequence are possible and which of the following probe sequence are not possible. Right. So which means let's examine this option A. Actually, this is a good question, and there has been many such kind of questions in GATE. So now we will see that how these questions could be very easy if we apply, one simple trick or one simple intuition. So I will tell you one very simple intuition. Okay, based on that you can easily solve these kind of questions. So basically, let's suppose there is a 40 43 you want to search, right? So they are saying, is this possible to get 61 at the first place? Yes, it is definitely possible to get 61 at the first place, right? I mean, whenever you are searching for 43, in your binary search tree, 61 could be the root. I mean, there is no problem in that, right? Then, okay, don't worry about these numbers. Then tell me, you will go to the left or you will go to the right if you are searching for 43. Definitely, you will be going to the left, right? Definitely, you will be going to the left. Okay. So, if you go to the left, you will be getting, they are saying you will be getting 52. This is definitely possible because you want to go left, right? Now suppose just for the sake of asking, I'm saying instead of 52 they write it 72. Is 72 possible? I mean, after 61 can you encounter 72? Tell me. See, 72 is not possible. Can you tell me why? Because you can very easily see that after 61 you will go to left. Okay, now we will go to left because we are searching for 43. So because we are searching for 43, hence we will go to left. Okay, and in left 72 cannot be possible, and in left 72 is not possible. Okay, is this clear to everyone? See, if they write 72 here, then directly I will say A is not possible. Okay. But since I will go to the left, so that is why I will say that since they are writing 52, 52 is definitely possible. Okay, 52 is possible, but 72 was not possible. Now let's just see one more thing. Okay, suppose here I will examine other options also. But suppose here 72 is only there, but instead of 43, they say I'm searching for 80. Let's suppose I'm searching for 80. Then tell me, is this 72 possible? If I'm searching for 80, that is this possible that I first see 61 and then I see 72? See, after seeing 61, I will be going to write. I will go to write for 80, right? And in right, 72 is definitely possible. And in right, 72 is possible. So it is all the matter of numbers. If they are writing 80 here, then 72 is possible. If they are writing 43 here, then 72 is not possible. If they're writing 43 here, then 52 is possible. Okay, because I will be going to the left. And in the left, 52 is possible. Okay, I just need to check that, okay, where I will be going. And in that particular position, say you will be deciding where you will be going based on this number, right? You will go to the left or you will go to the right. So this number, this will decide you will go to the left or right, right? This will decide you will go to left or right. Okay, so this number is very important here. Now you can see 61 because 61 could be the root. Okay, so suppose this is the root, so you can see 61. That's not an issue. Okay, suppose this is the root. And then after that, can you see 52? Because I will be going to the left, that's why I will be seeing 52. Now you tell me, you will be going to the left or you will be going to the right? Where you will be going? You will be going to the left. On the left, can you see 14? Definitely, right? We can definitely see 14. So I will be going to the left. Now, can I see 14? Yes, no problem, right? Now, can I see 17? Now I will be going to, again, tell me I will be going to the left or right. This time I will be going to the right, right? This time I will be going to the right. So now, if you go to the right, then can you see 17? Yes, 17 is definitely possible. I mean, it is greater than 14 and you can definitely see 17 in this way. I mean, there could be other branches, there could be other tree. Okay, I'm just seeing the path in which you are traversing. Okay, there could be other things, right? But let's not worry about those. 40 is possible. After 17, is 40 possible? Yes, right? Because you will be going to the right, and if you see that, okay, 40 is possible, yes, because this is lesser than all of this, greater than this, and 40 is possible. And then you get 43. Yes, you will, since you will be going to the right, you will be getting 43. So basically, this is definitely possible, right? I mean, this sequence is definitely possible. Okay. So I got to know that A is possible. A is possible. Now let's just check, is any other sequence possible? For example, I want to check for B. Okay, suppose I want to check for B. See, I will take at least 5 to 10 minutes maybe, okay, to explain this question, because there are many questions after this particular year. So this has been asked in 1996, and I think there might be 7 to 6 questions, 7 to 8 questions, or maybe 6 to 7 questions at least get asked based on this concept. Okay, so we will also learn some trick. Okay, we will also learn some very nice trick, or you can say very nice observation. Okay, we will see very nice observation to solve these kind of questions, right? How many of you have already seen these kind of observations from my lectures? Do you know that trick? Okay, let's just talk about the option B first. Okay, I'm going first step by step, then I will tell you the trick. So is 2 possible? Yes, definitely 2 could be the root. Is 3 possible? So first tell me, you will go to the right or left? You will go to the right, so 3 is possible, right? 50 is possible? Yes, since you will go to the right. Is 40 possible? Now you will go to the left, so yes, 40 is possible. Now, is 60 possible? Is 60 possible? You will go to the right, that's fine, right? But after 50, once you have gone to the left, once you have gone to the left, right? Then is 60 possible? Tell me here. So the answer is no, right? After 50, 60 is not possible because you will be going to the left. So because of this combo, okay, this combo is actually a deadly combo. Okay, I mean, in between 40 is coming, it doesn't matter. It could be 30, it could be any other number lesser than maybe 43. So basically, this 50 60 is a combo. I mean, after 50, 60 can never come. 60, this can never happen. Because at 50 you will go to the left, and once you go to the left, okay, in this whole world, इस पूरी दुनिया में 50 से छोटे ही हैं, 50 से बड़े नहीं हैं. In this whole world there are only numbers which are lesser than 50, not greater than 50. Okay, so this particular thing is not possible, which is 50 and then 60 is not possible. Now you see that I'm very close to tell you the observation, or very close to tell you the trick. With that trick, we don't have to draw the tree. Okay. So one observation is that after 50, 60 is not possible. This can never happen. Okay. Why that is the case? Because after 50, you will go to the left, and and on the left, lesser than 50 is only possible. Right? For example, lesser than 50, basically 40 is possible. Okay. 43 is possible. But 60 is not possible here, right? Because you will go to the left. Okay. Now let's just see option C. Okay. Now let's just see option C. So currently I will just tell you, I'm just trying to make a little bit of intuition. Maybe you have got little bit, but don't worry. I will tell you the complete trick. But before that, let's just talk about the option C. Okay. So what does option C says? It is saying 10, 65, 31. Okay. So which means, is 10 possible? Yes, 10 is possible. Okay. Why not? Right. 10 is definitely possible. So after 10, you will go to the right. Is 65 possible? Yes. Right. On the right, you will be seeing 65. After 65, since you will go to the left, is 31 possible? Yes. Right. After 31, you will go to the right. Is 48 possible? Yes. After 48, you will go to the left. Is 37 possible? Yes. Right. So 37 is possible, and then 43 could be possible, right? Okay. So C is also possible, right? So A was possible and C is also possible. So if you check the answer, so B and D are not possible. Okay, they are asking for the not possible, right? So C is possible. Okay, C is possible. Let's just check about the D. Okay, let's just check about the D. So D is saying 81. Now you will go to the left. On left, 61 is possible. And on now you will go to the left. On left, 52 is possible. Now you will go to the left. Then 14 is possible. Now you will go into the right, and right 41 is possible. So D is also possible. Okay. Now let's just talk about the option E. Right. So now let's just talk about the option E. So I will just tell you the trick in one moment. In option E, they are saying 17 is there, right? And then after 17, you will go to the right. That's for sure. Then 17, 7 is possible. 77 is possible. Then after 77, you will go to the left. Then 27 is possible. That's fine. Right? Then 66. Is 66 possible? Yes, you will go to the right of this. 66 is possible. Okay. Then is 18 possible? See, after 77, you will go to the left. So that's fine. Like 18 is possible till this point. But once you are at 27, then you will go to the right of 27. So if you observe, because of this 27 you have already seen, then 18 is not possible after that, because you have already went to the right. So this combination is deadly, 27 to 18, right? I mean, because of this, once you are 27, since you have made the decision to go to the right, then after this 18 is not possible. Yes, great. So Utkarsh is saying that cause of 27, 18, we cannot see 18, right? So this again, this is deadly combination, or this is not possible, basically, you can say. Okay, this is a trap. Now, now if you observe in option A and option E, what is happening? See, in option B and option E. So let me just copy this, and let me tell you what is happening here. So if you observe, okay, if you observe what is happening, let's just see. See, here in this option, in this B, 50, 60 is a wrong or deadly combination. Okay. After 50, you've already went to the left. then you cannot see the number which is greater than 50, right? You cannot see the number which is greater than 50. After 27, you have already went to the right, then you cannot see the number which is lesser than 27. Okay. See, here the greater than number is not possible. Here the lesser number is not possible. Okay. So can we make, some conclusion, some final conclusion? The conclusion is that since you're looking for 43, okay, then whatever numbers are lesser than 43, see, this is lesser than 43, this is lesser than 43. Okay. Lesser than 43 numbers should be in the increasing order. Okay, which means once you have seen 27, then you cannot see a number which is lesser than 43 and lesser than 27 also, which means let me just simplify this. What do I mean to say? That, see, here, let me just copy this question one more time. Whenever you have any sequence to deal with, okay, whenever you have any sequence to deal with. So suppose this is the sequence that you have to deal with currently. Okay, option A. Suppose option A is the sequence which you have to deal with currently. So yeah. So whenever you have any sequence to deal with, what you need to do, you need to divide the sequence into two parts. Okay. So let me just tell you what do I mean by that. See, suppose you have this sequence which is option A. Just give me a second for now. I want to have monotonous colors. Okay. Suppose you have this, which is option A, right? Now here in the option A, you have 61, 52, 14, 17, 40, and 43. Now divide this into two parts, okay? The numbers which are greater than 43 and numbers which are lesser than 43. So what are the numbers which are greater than 43 and what are the numbers which are lesser than 43? So let's just divide it into two parts. Greater than 43 is basically 61, 52, okay, and lesser than 43 is 14, 17, and 40. Okay, so this is greater than 43, this is lesser than 43. Now the greater than 43 numbers should be in the decreasing order actually. Okay, because once we have seen 61, then we will go to the left. So I cannot see number which is greater than 61, right? So whatever is the number lesser than 43, these are the numbers lesser than 43. Lesser than 43. Okay, these are the numbers which are greater than 43. So lesser than 43. Oh, sorry. I'm really sorry. So basically, these are the numbers which are greater than 43. Okay. So these are the numbers which are greater than 43. These are the numbers which are lesser than 43. 43 is important actually. Okay. Because I'm searching for 43. Now tell me, if these are the lesser than 43, once you have 61, okay. Once you have 60, then you will be going to the left. Now you will be only seeing lesser than 61 only. Everything actually should be the lesser than 61 here. Okay, everything should be the lesser than 61. You cannot, because you have decided to go to the left. Okay, so particularly you just filter it out into the two categories. Okay, 61, greater than 43 and lesser than 43. So if it is greater than 43, the greater than 43 numbers should be always in the decreasing order. Okay, you will be seeing the lesser numbers. Okay, and if it is lesser than 43, then it will be in the increasing order. This should be in the increasing order. Okay, this should be in the increasing order, and this should be in the decreasing order. So this is very important observation that we are making here. See, you just divide any sequence into two parts. For example, if you want to check, see, it should, since it should be in the decreasing order, it is in increasing order, so that's fine, right? I mean, this is basically this is possible. Okay, so they are asking which are not possible. So basically for the not possible, B and D are there, but let's just check B and D also. Okay, so let's just check B first. So just divide into two parts. Lesser than 43, greater than 43. This is 50 and this is 60. Okay, lesser than 43 should be in the increasing order. Okay, yes, this is in the increasing order, that's fine, but it should be in the decreasing order. Okay, so this is not in the decreasing order. Okay, so you can say this is not in decreasing order, hence option B is not possible. Okay, is this fine to you guys? So basically, this should be in the decreasing order, because once you have seen the 50, then you will go to the left and you cannot see any number which is greater than 50. Actually, any number here cannot be greater than 50. Okay, so similarly, after 2, you have already went to the right, so any number cannot be lesser than 2. Okay, like that. But we can still divide into two parts and then we can talk about it. Okay, for example, for option C, just divide into two parts. One is 10, 31, 37. Another one is 65, 48. Right? Now just tell me, is these are the increasing order? Yes, right? These are in the increasing order. Okay. Is these in decreasing order? Yes. So that's fine. I mean, there is no problem in that. Okay. So similarly, quickly check for other options. So let's just check option D. In option D, this is 81, 61, 52, and then you have yeah, greater than number are these, lesser number are these. Okay, lesser numbers are these. So is this possible? Yes. So it is in decreasing order, this is in increasing order, so this is definitely possible, right? What about the option E? So let's just quickly check for the option E also. Divide into two parts. One is 17, 77, 27. Sorry, lesser than, right? So lesser than is 27, 18, and here greater. So 77, 66. Okay, these are the numbers. So see, this should be in the, see, you don't have to remember whether it should be in the increasing or decreasing order. Once you divide, then you can question yourself. Okay, then it is easy to see actually. I mean, instead of looking at the whole sequence, you can understand like this. Instead of looking at the whole sequence, I'm first looking at the parts. Okay, so in the parts, if you see any counter example, then it is not possible. Okay, so which means that after 77, whatever is coming in the between doesn't matter, but after 77, is this possible to see 66? Yes, it is possible. I mean, so basically these numbers, I mean, the greater numbers should be in the decreasing order. This is possible. But after 17, you will go to the right. You will be seeing 27. But after 27, can you see 18? See, you will go to the right. So 27 and 18, this is basically in between, anything can come. But 27 and 18, this is a deadly combination. Okay. This is not possible. Okay. So basically, you will say this is not possible. So basically, you will divide it into two parts, and you will say that, okay, if the lesser numbers are in the basically increasing order, okay, because if it is lesser, then you will go to the right, and it should increase only. So basically, everything here has to be greater than 17. And anyway, like I'm only checking these. Okay, I'm not checking. See, if you are a little bit confused that why I'm not checking 17 against this 77 and against this 66, then anyway it is greater, right? Anyway it is greater, because these are anyway greater than 43 and these are lesser than 43. So the relative ordering is anyway happening. I mean, you don't have to check between these two. Okay, you can just check between these. So I hope you are getting my point, that just divide it into two parts. Okay, and then you can check the subsequence. Okay, if subsequence is not violating, then it is fine. Okay, if subsequence is violating, then it is a problem. If it is not violating, then it is not a problem. Which means, see, let me tell you one nice thing. Suppose, okay, suppose I give you these numbers. Okay, let me ask you another question actually. Okay, suppose I give you these numbers. The numbers are basically these. Let's suppose it is not option or something. This is the different question. Okay, suppose they say that these are the numbers, not in the order, in the sense that these are the numbers that you have. Okay, don't worry about the 43, because I have another question for now. Okay, so suppose these are the numbers which are in the which are this. These are not in any order or something. So 61, you can write 52 first. Okay, I mean basically I'm asking another question. So they are saying that how many probe sequences are possible if you are searching for 43 with these numbers. Okay, the question is that question is very different, and this question is very unique. So they are saying how many probe sequences are possible with these numbers if you are searching for 43. Okay, so let's just check. See, what are the numbers greater than 43? Numbers greater than 43 are 52 and 61. So basically, this should be in the decreasing order. So 61 and 52 should be in this order. Okay, I'm just writing the orders. Okay, I have to make sure this should be in this order. What are the numbers which are lesser than 43? It should be in the increasing order. So which means 14 and then 17 and then 40. This should be in this order. Okay. I mean, this is not any order. So you can even write 17 first and then 14. Doesn't matter. This is just some numbers. They are giving you some numbers. And then they're asking that how many probe sequences are possible if you're searching for 43. Then this question is very different. And let me just, go to the next page to explain this. So basically tell me if I give you this probe sequence. Okay. Let's suppose I give you this probe sequence 14. After 14, let's suppose I write 61. Okay. And after 61, let's suppose I write 17, and then let's suppose 40, and then I write 52. Okay. Is this sequence possible? Tell me. Is this possible? Is this probe sequence possible? You can quickly check. Okay, let me do one thing first. Let me basically, check using the bigger method. Okay, let me quickly check using the bigger method. So, which means let's just do one thing. See, is 14 possible? You will be seeing the 14, and then you're searching for 43. Remember, okay, 43 is our number. Okay, to or like which we are searching basically. Okay, so you will see 14, that's very much possible. Then you will go to right, then you will see 61, that's very much possible. Then you will go to the left, then you will be seeing 17, it is also very much possible. Then you will go to the right. On the right, 40 is definitely possible. And on the from 40 you will go to the right again. Okay, because you are searching for 43, and then on the right 52 is definitely possible, right? Okay, so basically it is possible. This sequence is possible. Okay, one other way to check is that whatever numbers which are greater than 43 should be in the decreasing order. Whatever the numbers which are lesser than 43 should be in the decreasing order. So basically, if I give you these numbers, then the moment I'm making sure 61 and 52 is coming in this order, and these three are coming in this order, then in between I can plug in anything. Okay, and that particular sequence is possible. So basically, if I just ask you, okay, is this sequence possible? Then you will say yes, because that's I mean that I'm maintaining the order. Okay. Suppose if I ask you, is this possible? 61, 14, 17, 52, 40. Is this possible? So you just check. Is 61 and 52 in the order? Yes. Okay. Is 14, 70, 17 and 40 in the order? Yes. So this is also possible. Okay. Now suppose if I ask you, is this possible? 52, 14, 17, 61, 40. Is this possible? So you will say that since this is not possible because this is not following the order, right? So this is not possible. Okay. So I hope you're getting my point. Basically, given any numbers, you can even tell that how many sequences are there. Okay, this is not any more binary search tree question. This is basically related to combinatorics. Can you tell me how many proof sequences possible? Now, can you answer me this question? that how many probe sequences are possible with these numbers? How many probe sequences are possible? You just need to check that 1, 2, 3, 4, 5 are there. So 5 factorial, okay, divided by this is 2 factorial because this is not possible. So you cannot overcount, and this is 3 factorial, right? Which means 5 into 4 divided by 2, which is basically 10, right? Is this fine to everyone? Let me know. Okay. You can even tell that how many probe sequences are possible. Will you believe that this particular question, that how many probe sequences are possible, has already been asked in gate one time? And if you don't have this this understanding, okay, exact this level of understanding, you cannot solve that question. So let me show you that question actually. So there was already one question related to how many probe sequences are possible. Hi everyone, can you hear me? Just hello. So sorry, there was some problem. Okay. So there has already been one question. Um, yes. So in GATE 2007, that question has been asked. Let's just solve this question. Okay. So basically, I was about to solve this question a little later, but you can solve this question now also. Okay. So they are saying, see, this question has got 213 upvote. This is, one of the, top upvotes. Basically, 213 is too much on the gate overflow, right? Okay. So what they are saying, when searching for the key value 60 in the binary search tree, node containing the key values 10, 20, 40, 50, 70, 80, 90. So 30 is not there. Okay, 10, 20, 40, 50, 60, 60 anyway we are searching are traverse. Not necessarily in this order. So basically they are saying that these nodes are traverse. How many different orders are possible in which these key values can occur on the search path from the root to the containing node the value 60? Okay, then you can divide this into two parts, okay, two groups. One are greater than 60 and one are lesser than 60. So 10, 20, 40, 50. These are the lesser than 60 and greater than 60 are 70, 80 and 90. Okay. Now, this should be in some order, increasing order, and this should be in the decreasing order, which means 90. I mean, the order could be 90, 80, and 70. So basically, this will be the order. Okay. Here, this will be the order. Okay. In decreasing order, it will be in the increasing order. So anyway, so basically, these are 4 and 3, 7 numbers are there. 7 factorial divided by. Can you solve this question? 7 factorial divided by, tell me. 4 factorial, because this is overcounting. Okay, this is a combinatorics question. So overcounting means that basically 7 factorial already counting all the possible combinations. So basically I'm just dividing whatever is overcounted. So overcounting is one of the method to solve these kind of questions. This is one of the very basic problem from the combinatorics. You must have already done this. And this is 3 factorial. If you solve this, you will getting 7 into 6 into 5 and 7 into 5 because 6 is 3 factorial. So 35 will be the answer. Okay. So have you understood this? See, this is one of the, you can say, top voted question on the Gator flow, and on the answer also. On the answer also, they have 2 to 5 upvotes. Okay, so which itself is saying that this question has been very popular among Gate aspirants. And this question you can solve only after this level of understanding that you have to divide into two parts, and then this order must be there, strict order, and this order must be there. So these two orders must be there. Okay. So let's just read the answer here. So what this answer is saying, in binary search tree, if we go from say 10 to 40 while searching for 60, we will never encounter 20. Yes, so we are going to 10 to 40 while searching for we will never encounter 20. So 10, 20, 40, 50. So basically they are saying after 10, 40 and 20 is not possible. Something like that they are saying. Okay. So basically this is the only order possible. Similarly, this is the only order possible. Okay. But you know the trick, right? I mean, basically you have to divide into two parts. One is lesser than 60, one is greater than 60, and lesser than 60 has to be in increasing order, greater than 60 has to be in the decreasing order, and that's all. Okay. And then you can solve these kind of problems very easily. How many probe sequences are possible? This is also a very nice problem, right? So now I hope you have understood the whole part of this, right? Now let's just move to the next question. So we have solved one of the very popular question also. How many probe sequences are possible? See, the numbers are also, too much like numbers are also not very close. I mean, this is like too big number, right? What is 7 factorial, by the way? Maybe 7 factorial could be something like this. So that's why they have put it like this. Okay. Okay. So now let's just see another questions. Okay. Now let's just see this question. So this is next question. Let's just try to solve this question. So by the way, I hope you understood the questions till now, right? Okay. So what this question is saying, a binary search tree contains the value 1, 2, 3, 4, 5, 6, 7, 8. The tree is traversed in pre-order and the values are printed out. Okay. Which of the following sequences valid output? So they are saying that there is a binary search tree that has these values. Okay. Now the tree is traversed in pre-order and the values are printed out. So which of the following is a valid output? So basically, in all of these options, you can see that they are saying in the, by the way, you remember the pre-order, right? It is basically root, left, and right. Okay. So in all of the options, they are saying 5 is basically one of the root. So basically, that's fine. Okay. So basically, if you write 5 as root, now, because since it is binary search tree, on the left, okay, whatever is on the left, right? So you will be first basically writing all the things on the left here, then you will be writing all the things on the right here, right? So on the left, the numbers will be lesser than 5. So basically you can say since 5 is a root, so here whatever is going to come, okay, so these are you can say lesser than 5, right? Now, now these are the numbers which will be greater than 5. Okay. I mean, these are the numbers which will be greater than 5. So basically, first all the lesser than 5 numbers should come. See, this is wrong, right? I mean, first all the lesser than 5 numbers should come. So B cannot be the answer. B cannot be the answer. Okay. First, all the lesser than 5 numbers should come. Right. So B cannot be the answer. This might be. We will see. Okay. So, but B cannot be the answer. Right. And then if we check that, then basically first all the lesser than 5. Okay. So anyway, B is B. Let me just remove this B. So first all the lesser than 5 and then greater than 5. Okay. So these should come. Now, if you talk about greater than 5, in the greater than 5 also, okay, these are the only three numbers, 6, 7, 8. So in the greater than 5 also, if let's suppose 7 is the root, okay, then lesser than 7 should be coming. Is this lesser than 7? Okay, don't worry about the other numbers. Okay, don't worry about the other numbers. You just focus on 7, 8, say 6, 7, 8. If 7 is coming first, which means 7 is the root, then lesser than 7 should be coming. Okay. See, lesser than 7 is 6, right? So is this coming first? No. So that's why A is not the answer. A is not the answer. Okay. If 6 is coming first, then lesser than 6 is the left is anyway null. So on the right, Okay, on the right, greater than 6 will be coming, so 6 7 8 is possible. Now if 7 is coming first, then 7 8, I mean this is possible basically. So if 7 is coming next, then after 7 you can definitely have 8, right? I mean if left is not there for the 7, then you can have 8. So basically for 6 also left will not be there, for 7 also left is not there. Okay, so you can have 8. Let's just check option D. In option D is saying 7 is coming first. Okay, but okay, we also have to check these things. I have not checked these things for now, but basically you are saying that 6 7 8 is possible, and similarly if 7 is coming first, then lesser than 7 and greater than 7, okay, is here. So basically this is also possible. I mean, you have not we were not able to filter out among C and D using this 6 7 8. So using the 6 7 8, we were able to filter out only A, right? Is this possible? You are having 6, and then let's suppose lesser than 6 is anyway not there. So on the right, you will be having 7 and 8. Yes. So this is possible. Now let's just check between C and D. Okay. So if 5 is a root, 5 is a root, then let's just check, is this sequence possible? Okay, so then basically 3 will be the left root. In both of the things, 3 will be the left root, which means, see, whatever number is coming here, 5, because it is basically root, left and right. Okay, this is the thing that we have. Now basically if we are having, let's suppose, let me copy C and D. Okay, in C and D both the options, 5 is a root, right? And then you will go to the left, right? And whatever is the next thing is basically recursively, you can say it is always the root. Okay, it is always the root. Okay, yesterday also we have seen that in the pre-order, these two numbers always say that this is structure. Okay, so which means in any pre-order you will whatever the first two numbers, basically they will make this structure. Okay, if left is not null, okay, if left is null, then obviously they will go to the right. Okay, but if left is not null, then they will make this structure. Okay. Okay, then is this 2 4 1 possible? So basically on the left of 3 you will be writing lesser than 3, you will be writing here greater than 3. So anyway 1 and 2 will come here, and greater than 3 4 will come here, right? So root and then left is 1 2. So basically left is 1 2, right? But here 2 4 is coming first. So left is 1 2 actually. So that's why C is also not possible. You're getting my point? See, let me go step by step. D is the only answer here because left is 1 2, 1 2 is here, 4 is here, right? Let me do this question once again, probably. Okay. So they are saying that which of the following is valid output? So by the way, correct answer is D, right? Correct answer is D. But we can do this question once again. See here, which of the following could be valid pre-order? Okay. Let's check option A. 5 is root. Okay. Basically in the pre-order, you have root, left and right. 5 is root, that's fine. On the left, you know that 1 2 3 4 will come because this is binary search tree. On the right, you know 6 7 8 will come, right? Okay, so 1 2 3 4 will come here, right? So basically 1 2 3 4 is anywhere here. So let's just deal with this small part, 1 2 3 4. I will deal with these two parts separately. I will deal with this part separately. I will deal with this part separately. Okay, so 1 2 3 4 I will deal separately, and say 6 7 8 I will deal separately. Okay, so let's just deal with 1 2 3 4 first. So currently I'm doing option A. Okay. Among this 1 2 3 4, who is the root? Again 3 is the root, right? Because root will come first. So I'm dealing with 1 2 3 4 only. Okay, because it is recursive. Okay, you can deal with this subpart because it is always recursive. So root, and then on the left, so basically ideally 1 2 should come and then 4 should come, right? On the left 1 2 should come, so left is anyway there. So now you can again deal with this 1 2 separately. Okay, so among this 1 2, okay, who is the root according to the pre-order? Root is coming first, so 1 is this, and then on the right 2 should come. Basically this 1 2 is definitely possible, right? and then 4 is separate. So basically you are dealing with 1 2 separately, 4 is 4 separately. So 4 is just one number and 1 2 are just two number. Actually, either if it is just one number, I mean the subtree is having just one number or just two number, so there won't be any problem. Okay, because 1 is the root, then 2 is either on the left or right based on the condition. Here we have binary search tree, so it is no right. But anyway, it will not cause any conflict. Okay, if it is more than two numbers, then we have to just check. Okay, so basically this is, I mean, because of this there is no problem. Now just check 7 8 6. So 7 will be the root. Okay, 7 will be the root, you can say. Now you can basically deal with 8 6 separately. 7 the root. On the left 6 should come, on the right 8 should come. So left should be coming first, but here it is right. So that is why this is not possible. Okay. What about the option B? So let's just check option B. Okay. So this is option B. In option B, they are saying that 5 is a root. Now, let's just deal with this separately. Okay, and then let's just deal with this separately. So, on the left, 1, 2, 3, 4 should be coming, but here it is 6. So, directly you can say it is not possible. Okay. Now, let's just deal with option C. Okay. Option C is saying 5 is there. On the left, 1, 2, 3, 4 is coming. On the right, 6, 7, 8 is coming. Okay. Now, 3 is the root. Okay. So, here again, 3 is the root. I'm just dealing with the left part separately. Okay, you can always deal with the subtree separately. So now, if 3 is the root, then on the left 1 2 should be coming, on the right 4 should be coming. So on the left 1 2 should be coming here in some order. It could be any order actually. Okay, doesn't matter. But here it is 2 4. So because of that, this is not the answer. Okay, this is not the answer. Now let's just check this option D. Okay, let's just check this option D. So in option D, they are saying, so 1 2 3 4 should be coming on the left and 6 7 8 should be coming on the right. Okay, so let me deal with this separately. So 3 1 2 4. Okay, so 3 is the root here, and 1 2 should be coming on the left and 4 should be coming on the right. So basically, as I told you, if it is just two numbers or just one number, it won't cause any conflict. So basically, this is, I mean, left is okay. What about the right? 7 is the root. On the left 6 should be coming, on the right 8 should be coming. So yes, left right. So actually this is not an issue. Okay, so this is definitely possible. Tell me if I've understood this. Okay, so basically only D is possible here. All other options are not possible. So this is actually very good question, you can say. Okay, so this is quite a good question, right? Okay, so basically D is the answer. Now let's just check this question, what they are saying. Suppose the numbers 751836092 are inserted in that order into an initially empty binary search tree. Okay, so they are saying there is initially empty binary search tree. The binary search tree uses the usual ordering on natural numbers. What does this mean? The binary search tree uses usual ordering on the natural numbers. What does this mean? It actually means, I mean, that 0 is basically lesser than 1. I mean, this is the ordering, right? Natural number ordering means 1, 2, 3. This is the ordering, right? 3. And you are also having the same ordering. I mean, this is actually useless line. I mean, by default, actually, we only follow this. But if you're confused, then it means that we are following this ordering only, 0, 1, 2, 3. I mean, basically, there is no other ordering possible. I mean, this question is not following any other ordering where 3 is basically lesser than 2. Okay, this kind of ordering is not there in general. Also in usual ordering also, this kind of ordering is not there. Okay, so basically they are saying you are just following the usual ordering. Okay, anyway, so this is not an important line. What is the tree? What is the n order traversal sequence of resultant tree? Okay, so they're asking for the n order traversal. Now, do you remember one thing, that n order traversal of binary search tree is always basically sorted. So let me just write one diagram here. Just a second. suppose this is the binary search tree, okay, and suppose your task is to find out the in-order traversal of that binary search tree. Okay, I will be just finding out. Suppose your task is to find out the in-order traversal. Now, for the in-order traversal, what we need to do? We basically need to write left first, and then root, and then right. Okay, but there is one more method to find out the in-order traversal. What is that? This is very, very interesting and very important also for some reason. I will just tell you that why it is, important, that you can just project. Okay, which means you can just write 1 here, 3 here, 4 here, 7, 9, 4, no, 12, 14, like this. Okay, you can just project. You can just project, and whatever you have is actually the in-order traversal only. Okay, project doesn't mean that you are basically, whenever you are making this binary search tree, then project doesn't mean that you can basically write, since 12 is on the right of 14, you can write 14 here. Okay, and then just project here. No, project means that you will be must making sure that, okay, everything on the of the left of 15 should be on the left. Okay, it doesn't mean that you are drawing like this. Okay, and then you are saying 15 will be projected and then 14 will be projected. So basically this is very nice trick to find out the in order of any tree. Okay, that you can just project, right? How many of you know this trick? I think most of you already know this trick, that you can just project, right? You can just project the numbers. Okay, okay. So basically you observe here that the in order traversal of any binary search tree is always sorted, right? Is always sorted. Because see, lesser than 1 is coming here, greater than lesser than 3 is coming here, greater than 3 is coming here, and 3 is coming here. If we just check this, then basically it is like 1 is coming first, 3 is coming next, then 4, and then followed by the same rule, right? So basically in order traversal of the binary search tree is always sorted, right? So this is very important rule that you might already be knowing, but still in order traversal. Okay, so they are asking for the in-order traversal. This is obviously unique. And what is that? It should be sorted. So I think C is the answer. Okay. Sorted in the increasing order. Okay. I mean, if they give you something like this, for example, 9, 8, 7, 6, then also this is not the answer, right? I mean, they give you in the decreasing order, then also it is not the answer. Okay. Sorted by default means increasing order only. Okay. I mean, decreasing order sorted is also called reverse sorted. Okay. Reverse sorted. I mean, sorted by default mean increasing order. Okay. So I mean here increasing order only. For the pre-order, you cannot have. So one of the comment is there that, sir, can we use this method in the previous question, that we are drawing the binary tree from the options and then checking that particular tree pre-order. If it matches, then it is the answer. So basically for the pre-order, it is not sorted. And okay, so you are saying that can we draw the tree and then just check if it is the in order is possible or not. So actually for this in order, like we just use the simple thing that in order traversal of binary search tree always sorted. Okay. Now let's just move to the next question. This question has been asked in GATE 2003, and this has got 107 upvotes. Okay, I mean the question itself has got 107 upvotes, but this question is actually very easy question. Okay, so what they're saying, let's just check. They're saying Tn is the number of different binary search tree with the n distinct element. Tn is basically defined as binary search tree, number of binary search tree with n distinct elements. Number of binary and distinct elements. So Suppose I say you one thing, okay? Suppose there is some binary search tree, okay? I'm trying to make one binary search tree. Now let's suppose this is the left of this. Let's suppose this is the right of this. Okay. So this is basically a binary search tree. This is the left part, left subtree, and this is the right subtree. But this is again a binary search tree, or any tree actually doesn't matter. But yeah, binary search tree for now. Search tree. Okay. So suppose Tn is basically the total number of I'm saying the total number of binary search tree with n nodes or n numbers. Then if these are the k numbers, then how many binary search trees are possible here? How many binary search trees are possible? Tk, right? If these are the k numbers, then how many binary search trees are possible? Based on this definition, okay? If this is just one root, then these will be n minus k minus 1, isn't it? I mean, the number of remaining, right? So how many binary search trees are possible here? T of n minus k minus 1. Is this okay to everyone? I mean, based on just definition, if this is having Tn, right? I mean, if n nodes are having Tn different number of binary search tree, then this must be having Tk and this must be having T of n minus 1 minus k, right? Now, if you fix this, okay, for example, let's suppose, let me have some example here. Suppose this is one binary search tree, right? Okay. Now suppose if I fix this left structure for now, okay, just for a moment, okay. So suppose I fix this left structure, then can you tell me how many binary search trees here? So basically there could be many binary search tree, maybe six. This with this three numbers actually six. This structure is also possible, and there are many other structures possible, right? And what if 7 is a root? Then this structure is possible. Okay, what if 7 is a root? Then after that, maybe 5 is coming and then 6 is coming. So there are many other, okay, doesn't matter. But let's suppose here, there are like whatever numbers of are there. So suppose using these, let's suppose 5 are possible, okay? Suppose 5 are possible using these, okay? Similarly, let's suppose using these 5 are possible. Then how many total? 5 into 5, isn't it? So basically for any fixed structure, these are the 5. Then for 5 structures, they will be 5 into 5. Basically, we'll be multiplying to get the total number of binary search trees. Isn't it? Is this okay to everyone? So basically, if I just ask you to write this recurrence, okay, then how you will be writing? How many total number of binary search trees are possible? You will say Tn, if Tn is the total number of binary search trees are possible, it must be equal to Tk into T of n minus k minus 1, right? Is this okay to everyone? Let me know. I mean, number of binary search trees here into number of binary search tree here. Okay, then only you will be finding the total number of binary search trees. Okay, number of binary search tree with the k nodes and number of binary search tree with the n minus k minus 1. Okay, but also you can change the root. So basically, let me go back to the question. And then you will see what they are trying to say. Okay, so they are saying that basically you are summing over all the nodes. So basically, maybe you can say the on the left hand side. Okay, on the left hand side there could be only one node. Okay, or there could be only two nodes like this, right? I mean, there could be even 0 nodes. On the left hand side there could be 0, 1, 2, 3 like this. Okay, I mean it will automatically shift it to the right. So basically, if this is n minus 1 nodes, then there will be 0 nodes here. So basically, you again have to sum that. Okay, k is the number for the k is the number of nodes on the left hand side, something like this, right? So they are taking, in this example, they are taking k minus 1, but that's fine. Okay, then they are asking the value of x. So basically they are saying that k minus 1 are the number of nodes on the left hand side or something. Okay, so the number of nodes basically could be ranging from 0 to n minus 1, something like this, right? So anyway, basically the point here is that that k, if k minus 1 are the nodes on either left or right, doesn't matter, on one of the side, and x is the node on right or on the other side, one is the node here, then what is the value of x? These are the number of nodes basically. Okay, so inside this T, you are writing number of nodes and distinct elements, which means n number of nodes. So these are the number of nodes. Number of nodes on left. Okay. If one is here, let's suppose they are dividing. Okay. So they are dividing into two parts, k and n minus k. Out of this k, one of this is root, and then k minus 1 is coming here, and then n minus k will be anyway coming here, right? So they are just asking, then what is the value of x? This is very, very easy question. So what is the answer? So all of this summation has to be n. Okay, all of the summation has to be n, which means k minus 1 plus 1 is basically k. So x plus k should be n. So what is the x? Is n minus k, right? See here. So answer is B. B is n minus k, right? I mean, this is a very simple question. They are not asking you to solve the recursion. Actually, you cannot solve the recursion. These are generally very complicated recursions. Okay, they are not asking anyway to solve this recursion. They are just asking you the value of x. Okay. So basically, they are having this recurrence on the number of nodes. Okay, x is the number of nodes on the right hand side. If the left hand side has k minus 1 nodes, then right hand side will be having n minus 1, n minus k nodes, right? That's very, very easy question. So the summation is for each node. If the node happens to be the root, then when the node is a root, it will have k minus 1 nodes on the left subtree, k being any number, and correspondingly n minus k elements on the right subtree. So the recurrence is something like this. Okay. So anyway, like basically, this recurrence, if you solve this recurrence, there is actually some typical formula that comes out. So if I remember correctly, it is, 2ncn divided by n plus 1, something like this. If you solve this recurrence, otherwise you don't have to solve this recurrence. Okay, don't worry about solving the recurrence and all. Okay, that's called Catalan number. Okay, so Catalan number, I think this comes out 2ncn n plus 1. Okay, something like this. Okay, but you don't have to solve this recurrence. You just have to observe this, that what is happening. Okay, now let's just go to the next question. The following numbers are inserted into the empty binary search tree in the given order: 10, 1, 3, 5, 15, 12, 16. What is the height of the binary search tree? The height is the maximum distance of leaf node to the root. So they are saying, they're just asking the height, right? So you can quickly insert and you can just check 10. After 10, they are inserting 1, and then they are inserting 3, then they are inserting 5, then they are inserting 15, then they are inserting 12, then they are inserting 16. Okay, so height will be determined by this, right? So this is 1, 2, 3. Height is 3. So what is the answer? 3. Okay, that's very easy question. You can easily solve this question. Okay. Now let's solve this question. This question has got 131 upvotes. Okay. And this question is looking very scary, but actually this is very easy question. Okay. Very easy and nice to understand. You can easily solve this question. Let's just see. A program takes the input, a balanced binary search tree with n leaf nodes, and computes the value of the function gx for each node x. If the cost of computing gx is this, okay, then the worst case time complexity of the program is this. So basically they are saying that compute the function gx for each node x. So you have n leaf nodes. Okay, so if n leaf nodes are there, okay, total you have n leaf nodes. So you can say here approximately you have n by 2 leaf nodes here, n by 2 leaf nodes here. Okay, I mean you have n leaf nodes. Total you have n leaf nodes basically, right? So these are the n leaf nodes. Now just look at this question carefully, what they are saying. They are saying gx is basically a gx, they want to calculate some function gx, right? So let me go to the next page. Okay. So they want to calculate some function gx. Now, what is that function they want to calculate? First, let me make the tree. Some tree. What is that function that they want to calculate? Can you tell me? Is this the function that they want to calculate? Is this gx? See, the trick or the main point here is that this is not gx. This is the cost of computing gx. You first have to understand this. This is not gx. This is not the function gx. Then what is gx? We don't even know what is gx. You getting my point? So what is gx is not our concern. Neither we know this, nor it is given, or nor we can know this. Basically, what gx is doing is none of our business. Okay. So basically, you can say what gx is doing. Okay. What gx is exactly doing? We don't know, right? So this we don't know. We definitely don't know. What we know is that if I want to calculate gx for this, okay, maybe I don't know what is gx. Okay, if I want to calculate gx for this, okay, maybe gx is like, maybe printing all these nodes, maybe gx is like summing all these nodes. I don't know actually. Okay, but if I want to calculate gx on this nodes, then it will be basically minimum number of leaf nodes in the left subtree. So number of leaf nodes actually here are n by 2 and here are n by 2. So minimum is n by 2, right? So minimum is anyway n by 2. So basically minimum is n by 2. The cost of computing gx at this particular node is n by 2 only. Is this clear to everyone? Okay. Cost of computing gx at this root node is n by 2. It should be clear to everyone. This is balanced binary search tree. So this n by 2 is the cost of computing gx at root node. Okay. Now tell me what is the cost of computing gx as this node? At this node, what is the cost of computing gx? See, it is basically minimum of this number of leaps here, number of leaps here. Actually, this is n by 4, n by 4. So it will be n by 4 only. I mean, it will be basically balanced. So minimum is actually doesn't matter if you don't add the minimum. Minimum is one of this. Okay, you can take any one of this. So these are n by 4, n by 4. This is also n by 4. This is also n by 4. So n by 4 will be the cost here if you want to compute the gx here, right? What is the cost of computing gx at this node? At this node again, n by 4 will be the cost because n by 4 minimum of n by 4 is actually n by 4. Minimum of number of leaps in the left subtree, number of leaps in the right subtree. So at this node also n by 4 cost, at this node also n by 4 cost, right? At this node n by 2 cost. Is this okay to everyone? Even if you have little bit of doubt, let me know. Okay. See, here in this question, students generally get confused. Okay. That what is this gx? Okay. Generally, students get confused. What is this gx? Okay. Gx is not basically, you can say, not basically gx is not we do not know gx, you can say in the easier words. So gx is not basically calculating any number of leaf nodes or something or like that. Gx is, we don't know what gx is doing. We just know what is the cost of doing gx. Okay. Is this understood? Okay. Okay. So I hope you're getting my point, right? So tell me what is the cost of computing gx here? So by the way, if you observe, okay, you can calculate the cost of computing gx at every node very easily. I will just tell you how. So if you observe one thing, see, Can you tell me, can you tell me, at this level, at the top level, which is having just one node, which is fine. At this level, what is the cost of computing GX? Total cost n by 2, right? N by 2. N by 2 is the total cost at this level. I mean, there is only one node, which is fine. But yes, n by 2 is the total cost of computing GX at this level. What is the total cost of computing GX at this level? Tell me. What is the total cost of computing GX at this level? Again, n by 2, right? Okay. So similarly, at every level, if you sum every level, okay, total cost of computing GX at every level is just n by 2. Okay, this is important observation. So you can say total cost of computing GX at each level. Okay, don't get confused by total. Basically, cost, I'm just writing the cost. Cost of computing GX at each level, or you can say total cost, doesn't matter. But total cost actually generally mean that for the whole tree. I mean, you might think I'm talking about the whole tree. So I'm just writing cost of computing GX at each level, just n by 2, right? How many levels are there if it is balanced binary search tree? See, they are saying it is balanced binary search tree. Okay, if you observe here, they are saying it is balanced binary search tree. So how many levels are there? What is the height? Log n, right? So, so at each level, if this is the cost, then what is the total cost of GX? N by 2 into log n, which means theta of n log n. Isn't it? Have you understood this question? Okay. This is easy one only, right? This is easy one only. Okay. So basically, what is the answer? B is the answer. Okay. B is the answer. So the thing is that GX is not, we do not know what is GX. The students think that how to calculate this GX. They think that this is GX and they try to optimize. Okay, that what could be the best algorithm that can optimize this or something. Okay, they try to use some kind of like hit and trial, or like they unnecessarily go in the different direction. The question is not saying that this is GX. This is the cost of calculating GX. This is the crux of this question. Okay. Now let's just see this. What they're saying. Post-order traversal of binary search tree produce the following. What is the in-order traversal they are asking? It must be sorted. So you can check what is the sorted. So an option is only okay. So A is the answer. Okay. So basically it should be the sorted, right? So you can check A is the only sorted sequence. So in order should be sorted. Okay. How many distinct binary search trees can be created out of four distinct keys? So, okay, let me just tell you this. See, let me tell you how many distinct binary search trees you can make with three keys. Okay, let's suppose 1, 2, 3 are there. How many distinct binary search tree you can make? So, see, let me first tell you how many structures are possible. See, one structure is something like this. Okay, which is definitely possible. Another structure, maybe this. Another structure, maybe this. Another structure, maybe this. Another structure, maybe this. So how many structures are possible? If you just talk about the structures, then there are five structures are possible. Actually, you can. I mean, now we have done it. Multiple times with this three. Okay, five. Actually, I mean, there's a Catalan number. Using the Catalan number formula, you can calculate that. If you plug in that three, you will getting five. But that formula we never have to remember. Okay. So with this three, anyway, the five structures are possible. Now, in how many ways you can populate this particular tree? Okay, you can take any structure. Let's suppose I'm talking about this structure. In how many ways you can basically populate this particular structure with 1 to 3? See, you can understand easily with the in order. So let's suppose. So basically, I mean, you don't have to do in order. Basically, I'm asking in how many ways you can populate. Let's not worry about the binary search tree. In general, if it is 1 to 3, then you write 1 to 3 here, 1 goes here, 2 goes here, 3 goes here. One way is this, right? Instead of 1 to 3, you can write 2, 1, 3. Okay, 2 goes here, 1 goes here, 3 goes here, right? So basically you can write 3 factorial combination, and then you can just reverse of projection or something like this, right? I mean, you can just plug in. So basically in 3 factorial ways we can populate this tree. Is this fine to everyone? In 3 factorial ways we can populate this tree. But if this is binary search tree, okay, tree, assuming currently I'm assuming no binary search tree constraint. But suppose if this is binary search tree, I mean, if I ask you that in how many ways you can populate such that finally it is binary search tree, then there is always one way. Given any structure, there is always one way. Because in order is sorted, right? In order is sorted. Earlier you were able to populate in any of these 3 factorial ways, but here you have to have just 1 to 3. Okay. This is the only way. This is the only way to populate given structure if we want to make it binary search tree. Is this fine to everyone? Let me know. Is this fine? Okay, right. So basically, for any given structure, there is exactly one way in which you can populate the numbers. Okay. There is exactly one way in which you can populate the numbers to make it binary search tree. But to make it a general tree, there are n factorial or 3 factorial ways. Okay. So if someone asks you that how many binary search trees are possible, then okay, if let's suppose someone asks you how many trees are possible, okay, how many trees are possible with these 3? 5 skeletons are possible or 5 structures are possible. Into each structure can be filled in 3 factorial ways, right? Each structure can be filled in 3 factorial ways. So that is why 5 into 6, which is 30 total binary trees are possible. Okay. 30 binary trees are possible. Is this okay to everyone? So suppose if I ask you that how many binary trees are possible, then you will say 30. Okay. So let me write here. Number of binary trees are possible with 1 to 3. Number of binary trees. Binary trees means labeled. Okay. I mean, if you are labeling. Unlabeled means a structure. Unlabeled always means structures. Unlabeled basically 5. Okay. Because 5 structures. Labeled basically 30. Okay. Binary tree means labeled basically. Okay. Number of binary trees possible with 1 to 3 or 30. Okay. Now, suppose they ask you unlabeled. In that case, you can say they are talking about the structures, or structures are basically 5. Okay. Structures manually you have to draw, or there is some formula, but don't worry about that formula. Okay. Structures manually you can draw. So there are like 5 structures possible. Okay. So number of structures, all maybe some people call it unlabeled. You can call it unlabeled binary tree. are 5. Is this okay to you guys? Is this okay? Let me know. Number of basically unlabeled 5 or labeled 30, right? Okay, I think I'm going a little slow, but let me just pace up the speed. So now if I just ask you binary search trees, what about the binary search trees? It is same as the number of structures, right? So how many binary search trees are possible? Equal to 5 structures, and each structure can be filled only in one way. Okay, so that is why 5 only. Okay, each structure can be filled only in one way. Is this okay to you guys? So each structure can be filled in only one way. Okay. Now in the question they're asking, so basically number of binary search trees are same as the number of structures, right? So in the question they're asking with this with the four numbers. Okay, the question original question was that how many distinct binary search tree created out of four distinct keys. So basically they're asking these are the four keys. How many binary search trees are possible? Okay, from here. See, you can think like this. There will be one root. Okay, root could be anything. Okay, either if it is 1 2 3 4. Okay, doesn't matter. Okay, then on the left, so basically now the three numbers are left to you, right? On the left you have to divide these three numbers. Okay, on the left there could be one number. On the right there could be two numbers, right? On the left, so basically you can say you have to divide these three numbers. Okay, on the left there could be one number. This is okay. Maybe let me start with 0. There is 0 numbers. These are the three numbers, right? I mean, for that, one should be there. If one is the root, then 2 3 4 will be on the right and left will be nothing, right? But anyway, like I'm just writing number of nodes. Okay, this is the number of nodes. So one node will be here. On the left subtree there could be 0 number of nodes. On the right there will be 3. This could be 1. This could be basically 2, because you have to divide three numbers, right? This could be 2, this could be 1, this could be again 3, this could be 0. So these are the possible number of nodes, right? Okay. Is this fine to everyone? Now tell me number of trees here. If how many trees are possible on the left with 0? Obviously no tree, I mean just one tree you can say. And here with this 3, we have seen 5, right? So here 1 into 5, right? Here 1 into 5. Let me write it on the right hand side. 1 into 5. Number of trees on the left side, number of trees on the right side. Here with this one, only one is possible. With the two nodes, I think with the two nodes, this is possible structure, this is possible structure, and there is no other possibility, right? I mean, there are only two structures are possible. I'm just counting the structures, okay? So with the two nodes, I think only two structures are possible. With the two nodes, two structures, with the one node, one structure, with the three nodes, five structures, with the zero node, one structure. Okay. So you can just sum it up. 5, 2, 2, 5. So 10 and 4 is 14, right? 10 and 14, 4 is 14. So 14 number, 14 is the correct answer. So basically they're asking for four distinct keys, but I have drawn for three only. Okay, I have drawn for three, and with this three, I know the answer is 5. Okay, for the three, I know the answer is 5, and then I went to 4. Okay, because of taking the help of 3. So basically, what I'm saying that let's suppose T is number of structures possible with n nodes. Let Tn is possible with n nodes. So what I'm saying, this T3 is 5, okay? And using this, I got to know T4 is 14. Okay. Is this fine to everyone? Great. Now let's just move to the next question. Actually, you can even find out for five. Okay, if these are the five things, then how many different structures are possible? So you can just break it down like this. Okay, you have to break down four. Four could be broken down like this: 0, 4. Okay, 1, 3, 2, 2, 3, 1, and 4, 0. Right. So basically here for 4 14 is the answer, and for 3 5 is the answer. So 1 into 14, 1 into 5. For 2, I think two structures, 2 into 2. For 3, 5 into 1. For 4, 14 into 1. Right. So 14, 5, 4, 5, and 14. If you sum it up, it will be 10 and then 28, 38, and 4, 42. Okay. So you can say with 5, 42 different structures are possible. Okay. 42 different are possible with 5. Okay. Anyway, you don't have to do all of this. I'm just telling you in case if they ask for 5 and you don't know the formula. Actually, intentionally, I haven't told you the formula, right? The formula is not needed because maybe they will not be asking any question based on the direct formula. Okay. They might trick you somewhere. So for that, you should be knowing the long method. Okay. So the long method is like this only, right? Okay. Now let's see this question. This question is again, I can say very interesting question. Okay. Or very nice question. This question is also very nice question. So do you want some break? Let me know. This has been 1.5 hours. Can we break for 5 10 minutes? Or maybe we can break after this question. I will give you some hint about this question and then we can have a break. Okay. Depending on you guys. So what they are saying, let's just see. By the way, this question has got 163 upvotes, and this question is also very nice question. Let's just see this question, what they are saying. So they are saying, suppose you are given some poster traversal binary search tree of n numbers. You have to determine the unique binary search tree that P has its poster traversal. What is the time complexity? So basically, they are saying that post order is given to you. Okay, post order traversal is given to you. In order you anyway know. Okay, in order you anyway know, which is 1, 2, 3, 4, 5, like this till n, right? In order you anyway know. So for n numbers, this is the n order, right? Post order is given to you. Okay. So post order is basically left, right, and root. Now they are not asking you to make the tree. I mean, they are saying if poster is given to you, okay, and in order is this. I mean, in order is anyway sorted. In that case, what is the time complexity to make the tree, right? So let me give you some hint, and then we will be having 10, 7 minutes break. Okay. So basically, the hint here is that what do you do if the poster is given to you, then based on this post order you say the last number, okay, last of the post order is root. Okay, so basically that's fine, which means you know the, okay, this is the last, and now you will be searching that particular number. Let's suppose this is any let's suppose this is 5 is a root or something. You will be searching here and then you will say that, okay, left of this is basically it will go to the left part. I mean, where is the 5 in the in order, you will be searching for that 5 in the in order, right? You will be searching for the 5 in the in order and you will say that, okay, now we know the left subtree and we know the right subtree, and we have to basically see that what is basically in the left subtree, what is the root, and in the right subtree also what is the root, right? We have to check this also. Is this fine? This is the way you do, right? Now, let's suppose Tn is the time complexity you take for the n numbers. Okay. Then I want to ask you that how to write the recurrence. Okay. For the n numbers, for this process, you will be taking Tn time. How to write the recurrence in the sense that how to calculate this Tn with respect to the subprograms. Let's suppose here you are getting k nodes. Okay. I mean, in the left there are k nodes. Here there are n minus k minus 1. Okay. Or yeah, that's fine. There are n minus k minus 1 here and there are k. Okay. So can you write like this that you have to again work for this k, you have to again work for n minus k minus 1, and you have taken the time to search for the 5 also. I mean, for this subprogram, I mean, you have divided into two subprograms, but for the subprogram also, you might have taken some time. And what is the time that you have taken? What is the time that you have taken? You have to search this 5, right? You have to search this 5. This is the time that you have taken. So how much time you have taken? Since this is already sorted, and to search this 5 in the sorted sequence, how much time you have taken? You can take log n time, right? Log n time. Is this fine to everyone? If you want to search this 5, right, you can take log n time. But the thing here is that, okay, there is very interesting thing, which is that they are saying that binary search tree has the n elements which are 1 2 3 4 5, I mean, which are 1 to n only. Okay, so those n elements that they're talking about, okay, those n elements they're talking about, they are not random elements. There are exactly 1 2 3 like this only. So suppose you have one in an array or in something, okay, 1 2 3 4 5 6 like this. Okay, suppose I ask you to find out 3. Have you you should you be doing the binary search, or you can directly tell that 3 will be at the third position, isn't it? So 3 will be at the third position, you can directly tell. Is this fine to everyone? I mean, you don't have to basically you don't have to do the binary search to find out 3. If this is exactly 1 2 3 4 5, I mean, numbers are exactly like this, then you can tell 3 is at the third position, 4 is at the fourth position, 5 is at the fifth position, like that, right? I mean, you don't have to even do the binary search here, because the numbers are 1 to n. That's the point. That's the very, very important key point here. Okay. So you don't have to do the binary search, which means log n is okay, but you can even do in I mean, you don't have to take the binary search here. You can do it in just constant time. Okay. Just one. So what I'm trying to say, basically, is something like this. So Tn is Tn minus k. So you can write Tk plus Tn minus k minus 1. Okay. Plus 1. Okay. The recurrence could be just plus 1. To divide into two parts, you are just taking plus 1. Let me know if that's fine. Okay. So basically you don't have to search 5 anywhere. It is just at the fifth position. So you can write plus 1. Okay. And then this is the k and this is n minus k minus 1, something like this, right? Then you can solve this recurrence. Now, okay. Now for this, you can easily see for this that see, if this is plus 1, then it will actually make this kind of recurrence very easy to solve. Let me tell you how. Let me just say the best case. Generally, we know the best case is that when the sequence is divided into half, right? N by 2, n by 2, right? So approximately n by 2. So basically, the best case is something like this. Tn is t of k is n by 2. Okay. Yeah, plus one minus one doesn't matter for the recurrence. For the asymptotic. Okay, plus one minus one doesn't matter. So Tn equal to T of n by 2 plus Tn by 2. This is kind of best case. The worst case could be when your root is such that you are dividing in such a way you just have one number here and something like n minus 1, n minus 2 numbers here and then plus 1. Okay. So this could be the worst case, this could be the best case. Now, if you calculate these time complexities of both of these cases, you will get to know that from here you are getting order of n or theta of n. Okay. From here also you are getting n. You can easily calculate. This is 1 plus 1 plus n times 1 plus 1 plus 1 substitution method 1 plus 1 plus 1 n times. This is also you can apply the Master's theorem and it will be theta of n. Okay. So basically in both the cases it is theta of n only. So how much time you will be taking? What is the time complexity from post order and period in order is anyway the sorted order. Okay, or in order is actually you don't have to do the binary search and all. You can do in the constant time. So using that, okay, using that for this particular question, okay, what is the time complexity for the most efficient algorithm to make the binary search tree is just theta of n. Okay, so B is the answer here. Okay, I am not written the answer, but yeah, answer is B. Okay, is this fine to everyone? That what we are doing? This is seeming to be very complex question, and it is actually very good question. Okay, it is actually very good question, but the answer is theta of n. Okay, so let's do one thing. Let's take a little break. Okay, of 5 minutes, or maybe we can continue for few more time, few more questions, and then we can take a break. Okay, because I still have many questions to solve, so we anyway have to take some break, but that's fine. Okay, let's just check this question. What this question is saying. This question has been asking GATE 2012. The worst case running time to search an element in a balanced binary search tree with n 2 power n elements is. Okay. So the balanced binary search tree is there. And then for the search, basically you will be searching with the height only, right? Log n. I mean, if this is balanced binary search tree, then the search will take order of h, right? H means log of number of elements. But here the number of elements itself are n 2 power n. Okay. So it is log of n 2 power n, which is nothing but n log n, sorry, log n plus log of 2 power n, which is nothing but n. So n plus log n, which is n. Okay. So C is the answer. This is easy question only. Is this fine to everyone? Okay. Now let's just see this question. What this question is saying: the pre-order traversal of some binary search tree is given. Which of is the post-order traversal? Okay, so using this pre-order, you have to make the binary search tree because in order is already known, right? So the pre-order is given to you, which is this, and in order is basically the sorted. So using that, okay, this is the pre-order. Now in order is actually looking like 10, 20, sorry, 10, 15, 20, 10, 15, 20, 25, 23, 25, 30, 35, 39, and 42, right? This is the in order. Pre-order says that root, root, left, right. Okay. So root is 30. We already got to know. Okay. And and 30, and then as I told you, then if it is binary search tree, then 20 will be on the left. So basically 20 will be the root of the left subtree. Okay, so this is like the first two numbers are basically like this only. Okay, if the pre-order is like this. Okay, so 30 you can log it, and based on this 30 you can say, okay, all of these will be going to the left, all of these will be going to the right. Okay, now again you can check that, okay, this 10, 15, among the all of this, basically 20 is the root. Okay, the next root is 20, so all of this will be in the left, all of this will be in the right. So basically 10 and 15 will be in the left, 15, and 23 and 25 will be in the right. Okay, among 10 and 15, which one is the root? 10 is the root, right? So 10 is the root, so you can write 10, and then 15 will anyway go to the right. So basically, I think you can solve this question, right? So 10 will be coming here, and 15. Among 23 and 25, 25 is the root, so 25 will be coming here, and 23 will be coming here, right? Okay. On the right hand side, this will be 35, 39, 42. Among this 35, 39, 42, which one is the root? 39 is the root, so 39 will be coming here. Okay, and then 35 and 42. Okay, so 35 is here and 42 is here. So this is the tree that we have got. Now you can basically make the post order of that tree. Okay, so now you can make the post order of that tree. So post order means left right root. Okay, now you can actually find out the post order. So basically this is the tree. Now if you find out the post order, it will be like this. Okay, so that's easy question only. Hope you understood. Now let's see this question, what they are saying. Which one of the following is the tightest upper bound that represents the time complexity of inserting an object into the binary search tree of n nodes? Okay. Which one of the following is the tightest upper bound that represents the complexity of inserting an object into the binary search tree? Okay. So for the n nodes, it could be basically the height could be it could be totally skewed, right? I mean, need not to be skewed. I mean, it could be like zigzag also. Okay, see, always remember this possibility of zigzag. Okay, I mean, for this question, it might not be useful, but for some questions, it is useful. Okay, it could be in any shape. I mean, if you want to, for the n nodes, if you want to have the height like n or n minus one, then this is definitely the possibility left or right is skewed. But apart from that, this is also there. I mean, some zigzag possibility. At every level, there is just one node. Okay, at every level, there is just one node. For example, okay, something like this. Now, obviously, order of n is the answer because the height could be as long as n, okay, or n minus 1. Okay. Now let's solve this question. This question is, I can say one of the most less understood question. Okay, among all the questions of binary search tree. Okay, so this question, like most of the people were not able to understand that how to solve this question, and on the gate overflow also, I was not able to find very satisfactory answer. I mean, I don't know who has given the top answer, but actually the detailed explanation is not there. Okay, for this question, let's see this question. So I can say this question is one of the very less understood question among all questions of binary search tree. Okay, let's just try to solve this question. What this question is saying. So, by the way, have you seen my lectures? Are you Go classes students? I mean, enrolled student. So we have one topic which is range search and binary search tree. So the topic name is range search. How many of you seen this lecture? Range search in binary search tree. Okay, so let's see what they're saying. They are saying, suppose we have balanced binary search tree holding n numbers. We are given two numbers L and H, and we wish to sum up all the numbers in T that lie between L and H. Okay, so they are saying, for example, this is some balanced binary search tree that we have, right? Now they are saying that we can have two numbers. Let's, for example, let's suppose, 8 and 23. Okay, 8 and 23. So between 8 and 23, whatever numbers are coming. So for example, this number, this number, this number, I think, yeah, these numbers are coming between 8 and 23. Okay, these numbers are coming between 8 and 23. So between 8 and 23, whatever numbers are coming, right? We need to sum all of these numbers. So how to find all the numbers which are between 8 and 23? This is the first question. Okay. And what is the time complexity? So basically they're asking the time complexity to find all the numbers between the given range, which is, let's suppose, which could be anything. For example, 8 and 23. So this is L and this is H. Understood? So basically the question is saying that we want to find out all the numbers between L and H. Okay. It could be any range. For example, here I'm just trying to show 8 and 23. It could be any range, right? And we want to find out all the numbers between L and H. And suppose these are the M numbers. They are also giving that suppose these are M numbers, right? Then and N is the total number of elements. Okay, N is the total number of elements. So n is the total number of elements and m is such numbers, okay, which are between L and H. Now, what is the tightest upper bound to compute this sum? Okay, let's just check. So suppose, let's just go step by step. Suppose here I ask you, you want to find out all the numbers between 8 and 23, suppose. Okay. First, notice one thing, that the numbers between 8 and 23 looks like this, right? So first notice one thing is that if you take the in order projection, okay, if you take the in order projection, then here the numbers are like this between 8 and 23. These are the numbers between 8 and 23, right? I'm just making a box. So basically the between 8 and 23, whatever the numbers, it will be in just one box. Is this possible that some numbers between 8 and 23 are here, some numbers between 8 and 23 are here? Is this possible? Is this possible to have some numbers between 8 and 23 here, some numbers between 8 and 23 here? Or in other words, is this possible to get, two boxes, basically some numbers here, some numbers here, like this, right? It is not possible. Why? Because since in order is always sorted, right? So whatever the box is there, right? There will be just one box. There cannot be two boxes because in order is sorted, right? So in between 8 and 23, okay, let's suppose this is in between 8 and 23. Okay, so here I'm having the range 8 and 23. So there will be just one box, okay, or in other words, there will be just one circle. Okay, there will be just one circle. Okay, for the tree, it is not possible that some numbers between 8 and 23 are here, some numbers are here, like this. Okay, it is not possible. It will be just continuous one circle. Is this possible? Tell me. Okay, I don't have the diagram, but yeah, it is possible to have two circles that, okay, these are the numbers between 8 and 23, these are another numbers between 8 and 23. Okay, in between some numbers are not in 8 and 23. Is this possible? No. So one thing is for sure, that whatever range we have, there will be only one circle. Okay, I mean, the numbers between 8 and 23, it will be just one circle. So now let's just do one thing. Let's just try to traverse this tree. Okay, let's just try to traverse this tree. Now suppose I'm here. Is this number between 8 and 23? If that is the number, I'm just following very simple rule. Okay, very simple traversal. See, currently I have not started my algorithm. Okay, let me just tell you my algorithm, which is extremely simple algorithm. Okay, it is just saying that if the number, okay, whatever the current number, if the current number, okay, current number is between, basically, let's suppose your range, which is, let's suppose, for example, 8 and 23. Okay, if current number is between your range, then go to the both side, left and right, both. Okay, then go to the both side. So I'm going to the both side. Okay, go to the both side. So 15 is here, I'm going to the both side. Why? Because this 15 is between 8 and 23. Now 7. Now 7, tell me, is this in between 8 and 23? No, this is here, right? I mean 7 is here. Basically, if you see the number line, 7 must be here and 823 must be here, right? And other numbers. So basically 7 is not in the range and also on the left. So if you want to find out 8 and 23, you will go to the left or right? You will go to the right. Okay, you will go to the right. Okay, you will go to the right. So basically you will go to the right. Now, this 12 is between 8 and 23. You will go to left and right both. And this is anywhere between 8 and 23. 24 is not between 8 and 23, but it is here. So you will go to the left. So you will go to the left. 24, you have traverse. So whatever you are traversing, I'm just circling it out, but I'm going to the left only. In between 8 and 23, I will go to the left and right both. Okay. So that's how I'm traversing. Is this fine to everyone? So how we are traversing, right? So if you traverse, okay, if you traverse, then this is the path that you will be basically getting if you traverse between 8 and 23, right? Now, given this, let's suppose I want to traverse between some other number. Let's suppose I want to find all the numbers between 2 and 28. Okay, let's suppose I want to find all the numbers between 2 and 28. I will go here. Since this is within the range, I will go here also. I will go here also. Okay. Since this is also within the range, I will go here also. I will go here also. This is also within the range. I will go here also. I will go here also. This is okay. Here I have a traverse, but it is not the answer. Okay, that's fine. Okay. This is also within the range. I will go here also. Here also. This is also within the range. Here also. Here also. Here also. Here also. I mean, basically, I might be visiting almost all the nodes, right? Okay. I mean, if this is basically more subtree, then I will not be going to the 29 because 20, right of 29, I will be only going to the left of 29 like this, right? So, but but basically, you can say if you are basically your range is 2 and 28, then these are your desired numbers, right? These are your desired numbers. Okay. So basically, at every node, if that is in the range, you are going both side. If that is not in the range, then either you are going to the right of that particular node. I mean, that node is pushing you to the right, or that node is pushing you to the left, right? So basically you can say that you will be getting, for example, here you have got some tree. It is basically pushing you to the right, suppose. Okay. I mean, let's suppose okay. So currently you will be going to the both side, left and right, but this is not there. Okay, that's fine. So what I mean to say that at every node, okay, at every node you will be making a decision either to go to the left or to go to the right or to go to the both side. Okay, or to go to the both side. Great. So let's just check how many nodes you will be visiting. If these are the M nodes that you are anyway visiting, so I mean M is the desired nodes, okay? In the range, if you have M, then anyway you will be visiting M nodes, okay? Are you visiting something extra? Yes, yes. What are the extra nodes that you might be visiting? See, for example, here 7 is extra. 7 was not in our search. I mean, it is similarly 24 is extra. So basically, at every level, at most you can get two extra nodes. I mean, one is pushing here, one is pushing here, right? At most you can get two extra nodes. For example, if you are searching something, let's suppose between 14 and 17, okay? Yeah, if you are searching something between 14 and 17. So for 14, you will say that okay, this is in the range. Okay, you will go left and right both. Okay, then this is not in the range. So if you are searching for between 14 and 17, let's suppose, okay, then this is in the range. You will go left and right both. This is not in the range. You will go to the left. This is not in the range. You will go to the left. You will go to the right. This is not in the range. That's fine. Okay, but yeah, you will be visiting it. This is not in the range. You will go to the right. So basically, the range nodes are basically this. Okay, this is in the range and this is in the range. Only three nodes are in the range, right? Otherwise, at every level, you are getting something like two extra, right? I mean, see, whatever skeleton you are getting, okay, so basically at the boundary you will be anyway getting 2, right? At each level anyway 2, right? Not more than 2. See here extra could be anyway at most 2. Here these are anyway within, right? These are anyway within, but extra at every level it could be at most 2. What I mean to say, that that if you are basically searching for any range, okay, then am nodes you anyway have to visit. Apart from that, at every level, either this node, okay, this node, if this is in the range I have already counted, okay, in M, if this is a range I have already counted. If this is not in the range, then see, actually it doesn't matter whether this is in the range or not. So see what I mean to say, that am nodes you are anyway visiting, okay. Now, at every level, you are also visiting two nodes. Okay, so 2h nodes also. So basically, m plus 2h. Now, at every level, whatever you are visiting, it could already be have counted in m. Doesn't matter. Actually, this is m or 2m. Actually, doesn't matter. Even if I'm over counting it one more time, doesn't matter. Okay, because it could be m, 2m, 3m. Doesn't matter. Because if I'm even over counting it, see, some nodes are here also or here also. What I'm saying, that I've divided the nodes into two categories. Okay, one category of the nodes are the nodes within the range. Another category of the nodes which are just helping me to push. Okay, just helping me to push. So at most two nodes are there at every level. They are just helping me to push. So that's why 2h. Now those helping me to push could be also in the range. Okay, this could also be in the m also, but it doesn't matter actually. Basically m in the range, and 2h could be the at most extra. Okay, 2h could be the at most extra. So basically m plus 2h is the total number of nodes you will be visiting. Getting, because m you have anyway have to visit. How I'm getting 2h? At every level you might be getting two nodes which are on the border and these are pushing. Now you may say, okay, that's already in the range. Suppose then you have already counted in this m. Actually these things doesn't matter. It could be like 2m, 3m. I have already, this is 3h, 4h, doesn't matter. Okay, so basically m plus 2h is my answer, which means that m nodes I have to visit anyway, plus 2h nodes are there which are helping me to push, or you can say these are the border nodes. Okay, so the range nodes, so you can say something like this. Or maybe I can copy one of this diagram. See, I mean to say that m plus 2h will be your answer. M is the nodes you anyway have to visit, right? 2h is the number of nodes that are helping me to push. Okay, so you can say number of border nodes, and these are the, you can say, range nodes. These m are the range nodes. Okay, so these range nodes, or in other words these border nodes could also be having some of the range nodes. Doesn't matter. Even if it is having all of the range nodes, doesn't matter. If this is having all of the range nodes, it is as good as saying that, okay, this edge already has, m. I mean, I'm already counting one more extra m. I'm counting, it doesn't matter. Okay, I'm counting two more extra m. Doesn't matter. Okay, so these are the number of border nodes and these are the number of range nodes. This I anyway have to visit. These are helping me to push. These border nodes are basically helping me to push, right? So m plus 2h is answer. Okay, so for the range search, okay, for the range search in binary search tree, you can say, you can say if m is number of nodes in number of nodes in range, and n is total number of nodes. Sorry, actually total number of nodes you can calculate given the, I mean, you have to calculate the height. Okay, so it will depend on the height. So you can say this is the height of the tree. Then what is the complexity? Order of m plus 2h or m plus h, doesn't matter. Okay, I'm writing m plus h. For if the tree is balanced, okay, then height is log n. If it is balanced binary search tree, in that case it will be order of m plus log n. Okay, if it is balanced, then it will be h is log n. If it is not balanced, okay, so if it is not balanced, in that case it will be, so basically it will depend on the height, okay, based on the height. So it is either m plus log n for the balanced, or it is m plus n for skewed or zigzag. Okay, something like this. So basically it will depend on the height. Now in this question, the question which is given to us, in this question they are saying it is a balanced, okay, it is a balanced binary search tree. So that is why m plus log n is answer. So if you say m plus log n, so c is 1, d is 0, and for the log n b is 1, a is 0, right? So m plus log n is your answer. Okay, so let me tell you that a is 0, b is 1, c is 1, and d is 0. Basically, if you just you know write this thing, for in general order of m plus h is answer. For balanced it is order of m plus log n. And from this if you compare, you will be getting from c, so c is 1 and d is anyway 0, and log n you will be getting from here, so a is 0 and b is 1. Okay, is this fine to everyone? Okay. So is this understood to you? Basically, just to revise, let me tell you in just one line that you will be visiting some nodes like this. I mean, if it is in the range, you will go into the both side, and then there will be at every level there are at most two nodes which will be pushing you inside. Okay, there will be exactly two nodes, not at most. There will be exactly two nodes. Okay, that will say. I mean, if it is in the range, that's okay. If it is in range, if you are going to the both the sides, you can consider that to be in the range. Okay, if that is not in the range, then you are going either to the left or right. So it will be at most, yeah, at most two, you can say. Apart from this M, there will be at most two H more nodes, right? That is basically helping you. Okay. So either you will be visiting both the sides. I mean, if it is in the range, you will be visiting both the sides. And if you are not visiting both the sides, then you will be basically going either to the left or right. So you can say it is a border node. Okay. Okay. And there could be at most two H border nodes, right? Now let's solve more questions. So this question has been asked in GATE 2015. Okay, let's just see this question. Which of the following is or are correct uh, in order traversal sequence of binary search tree? Okay, so for the in order it should be sorted. So that's why it is easy question, right? So basically, you can see whatever is the sorted. Let's just check the next question. What they're saying. What is the worst case time complexity of insertion and deletion of a key in the binary search tree? So it could be actually skewed, okay, or it could be zigzag also. Never forget the possibility of zigzag. Okay, so actually for these questions it doesn't matter, but you should always be having in the mind that for getting the height n or n minus 1, skewed is not only the possibility, zigzag is also the possibility. Okay, so order of n or theta of n. Okay, so B is the answer. See, always students actually always make the skewed, but they actually forget the possibility of zigzag also. Okay. Now let's see this. While inserting the elements 71, 65, 84, 69, 67, 83 in an empty binary search tree in the sequence shown, the element at the lowest level is okay. So basically 71 is here on the left. You will writing left lesser than 17, which means 65, 69, 67. This will be coming in the same order, and here it will be 84, 83, right? So you can easily make that tree, and if you make that tree you will be getting the answer. So basically 67 is the lowest level. Okay. So one of the student is asking that, sir, I have completed DA syllabus and I thought 50-60% course will be same in CS. Okay. So if you have already completed DA syllabus, then you should be focusing on DA only. If you have already completed DA, then just focus on the DA. Okay. Don't go to the CS now because you have completed the DA syllabus. Okay. It is not possible to cover CS syllabus, and DA syllabus both in just remaining time, because you anyway have to revise the DA syllabus also. Is this okay to you? Okay. Now let's see this question. Let's see what this question is asking. So before that, let's just take a break. Okay. So we will be just meeting after a few minutes. So maybe we will be meeting at 1:30. Okay. At 1:30 we will be meeting. Hi everyone. So let's now start. Okay. So let's see this question. So what they're saying, this question also got too many upvotes, and this seems to be a very nice question. So let's just solve this question. What they're saying, the number of ways in which the numbers 1, 2, 3, 4, 5, 6, 7 can be inserted in empty binary search tree such that resulting tree has height 6. Okay. See, if there are 7 nodes, then what is the possibility that resulting tree has height 6? See, this possibility is only there, I think, right? For example, it could be something like this, right? Or maybe let me make nicely 3, 4, 5, 6, and then 7. So these are the 7 nodes that we have, right? So this is one possibility. Is there any other possibility? Yes. So definitely there are like other possibilities which are something like this. So there is one more possibility which is something like this. 3, 4, 5, 6, 7. Is there any other possibility? Yes, it could be zigzag also, which means at every level there should be one. 1, 2, 3, 4, 5, 6, 7. Okay. I mean like this and like this. 1, 2, 3, 4, 5, 6, and 7, right? 2, 3, 4, 5, 6, and 7. Okay. So basically there are many possibilities. Now they are saying that if you have 7 nodes, okay, the question is saying that if you have 7 nodes, then in whatever the what is the number of ways in which we can insert such that we have height 6. So for the height 6, basically you will be having first first tell me whatever the possible structures are there. See, uh, one possible structure, as I told you, could be something like this, right? Now, in this structure, how many ways you can populate this structure if this is a binary search tree you need to make? For the binary search tree, you can only populate in one way. For example, if you have 1, 2, 3, 4, 5, 6, 7, right? Then 7 must be here, 6 must be here, 5 must be here, and so on, right? So if you want to make this as a binary search tree, then you can only populate in one way, right? Similarly, you can take any other structure. For example, this structure 3, 4, or maybe 3, and then 4, 5, 6, 7. Let's suppose this is the structure. Now tell me, among this 1, 2, 3, 4, 5, 6, 7, and how many ways you can populate it such that it is actually binary search tree? Then again the answer is one way, right? So how to do it? Basically, you can do the in-order projection. Actually, I just made it like this, but you can understand that like this, right? Okay. And then, I mean, these will be coming there. And yeah, so this will be coming here. You can just do the in order projection. Okay. So basically 1, 2, 3, 4, 5, 6, 7, which means 7 must be here. Okay. 6 must be here. 1 must be here. 2 must be here. 3 must be here. 4 must be here. And 5 must be here. Right. In this way only you can fill. Otherwise, there is no other possibility to fill. Okay. So basically, given any this skewed structure, there is only one possibility to fill. Or in other words, you can make this skewed structure based on this possibility only. First you insert 7, then you insert 6, then you insert 1, then you insert 2, 3, 4, 5. Okay. Then this skewed structure will be possible. Basically, the insertion order and skewed structure are having one-to-one mapping. Okay. So how many insertion orders are possible such that you have height 6 is same as saying how many height 6 structures are possible. Okay. So how many height 6 structures are possible? Can you tell me? See, if you're at this node, then there are two possibilities. Either you can go left or you can go right, right? So you can either go left or you can go right. So if you go left, so basically here there are two possibilities. I mean, at every node, at every level, I just want to fill one node. Okay. So there are two possibilities here. At this particular point in time, you have two possibilities. Here again, you have two possibilities. Either go here, here. You can go anywhere. Here again, two possibilities. Okay. Oh, sorry. Here again, two possibilities. Right. And here again, at this level also, you again have two possibilities, either go left or right. Okay. So here again, let's suppose I have taken this. So here again, two possibilities. Here again, you go either left or right. Suppose I go this, again, two possibilities were there. So 1, 2, 3, 4, 5, I have already filled. Let me fill two more. Okay. So here again, two possibilities. I can take any possibility. Let's suppose I am going here. Here again, two possibilities. So two possibilities here. Here again, two possibilities. Either go left or right. Let's suppose I am going left, or maybe I am going right. Okay, doesn't matter. So here two possibilities were there. Okay. Yeah. So basically, how many possibilities? 1, 2, 3, 4, 5, 6. So 2 power 6 possibilities are there. I mean, 2 power 6 ways I can make any zigzag. Okay. Maybe it is skewed, maybe zigzag, something like this. 2 power 6 ways are there. Ways are there. In which you can get the skewed tree. Right. So basically, you can say that for every way you can fill only in one possible way. For every structure, you can only fill in one possible way. So there are basically 2 power 6 possible insertions are there, such that you finally get the height 64. Okay. For example, for this, what is the possible insertion? See, everything here is on the left of this. So it must be basically everything should be lesser than some number. So it must be 7. Everything should be greater than this. It must be 1, right? Everything should be greater than this. I mean, this 1, 2, 3, 4, 5, 6, 7. 7 is already out. Everything should be greater than this. So 1 should be there. Everything should be greater than this. So 2 should be there. 3 should be there. Okay. And then if it is like this, then it will be basically 6. And then, uh, so lesser than 6 is, so everything should be greater than 4, and then it is 5. Okay. So actually there is only one possible way in which you can fill it. Okay. Or otherwise you can basically have in order. Okay. 1, 2, uh, sorry, there is something wrong I did, I think. So everything should be greater than that. Everything should be greater than, and then I think it should be 6, right? It should be 6. And then after that, everything should be greater. So it should be 3, then 4, and then 5. Okay. Or otherwise, you can simply take the in order. Okay. 6 and 7. So basically, there is only one possible way in which you can fill any given binary search tree. So how many possible insertions are there? 2 power 6, right? So 2 power 6 means 64. Okay. 64 possible insertions are there in which you can fill this tree. Okay. Or you can get the height of 6. Suppose if I ask you some other question, okay, maybe it will be more clear. Okay, it is little tough question. Okay, so I can say one trickier question. Let's suppose I ask you this question. You are given, okay, you are given 1, 2, 3, 4, 5, 6, 7. Okay, and you want to get the balanced binary search tree. This time it is balanced, okay, and you want to get balanced binary search tree. Balance perfect, or you can say perfect binary search tree. Okay, which will look like this. So basically 4 will be in the middle, and then 2 here, 1 here, 3 here, and 6 here, 5 here, and 7 here. Okay, suppose you want to get something like this. Okay, now here in this case they are asking, let's suppose, how many ways you can insert such that you get this. Okay, so number of possible ways you can insert. To get this. So basically, I want to get this. Let me just make it very clear. Okay. 2, 1, 3, 6, 5. I want to get this. So one thing is for sure that 4 should be inserted first, right? Should be inserted first, right? Now among this 1, 2, 3, or let's just talk about this. Among this 2 and 6, anything could be inserted first, right? Doesn't matter. Actually, if I compare this 3 and 5, okay, I mean, if I have to ask you that based on this 3 and 5, which should be inserted first? Okay, then it doesn't matter. I mean, basically 3 and 5 doesn't have any particular choice of ordering. Okay, that 3 should be inserted before 5 or like that. I mean, if once it is divided into left part and right part, then it will be separate problems. So basically I need to decide among 1, 2, 3. That 2 should be inserted first. Okay, then 1, 3 can be inserted in any way. Similarly, 6 should be inserted first, and then 5, 7 can be inserted in any way, right? Something like this. Okay, so basically you can say 2 should be inserted, and then 1, 3 probably you can insert in any way, right? Okay, and then here 6 should be inserted. 6 is fixed, right? And then 5, 7 you can insert in any way, something like this, right? Is this fine to everyone? And also this could be interchangeable. Okay, so first tell me if this is, let's suppose I fix this order. Okay, I fix this 2, 1, 3. Okay, so suppose I fix this as 2, 1, 3. Okay, I fix this is 2, 1, 3. I mean, let's suppose this is the only order. Okay, I will alternate this 1 and 3 later on. Okay, for now, let's suppose this is the only order. Here I am saying 6, 5, 7. Okay, let's suppose this is the only order. Although I know that 5 and 7 could also be alternate, and 1 and 3 could also be alternate. But let's suppose it doesn't matter. I mean, I will do it in just a moment. Okay. Then, since this is 6 number, so I can say 6 factorial divided by 3 factorial into 3 factorial are the ways in which these can be interleaved. Actually, these interleaving doesn't matter as long as I'm fixing this particular order, right? So if you check it, this is 6 into 5 into 4. 6, 5 into 4 is 20, right? Okay. So basically 20, right? In 20 ways, these could be interleaving. Is this fine to everyone? Now, is 20 my answer? Is 20 the final answer? See, in 20 ways, these could be interleaving, but I can interleave these also. I can basically permute these also. So 2 ways, and I can permute these also. So again, 2 ways, right? So basically, you can say 80 is the correct answer. In 80 possible ways, basically you can insert such that you get this balanced binary search tree. Okay, is this fine to everyone? In 80 ways, you can insert. Okay, so there are 80 ways to insert 1, 2 till 7 such that we get balanced binary search tree, right? Can you tell me some possible ways? So for example, one of the possible ways is that 4 is anyway I have to, I have to insert 4 first. Okay, so basically, can you tell me some of the possible ways? 4 I have to anyway insert first. Then, okay, after 4, I can insert, okay, among this, well, see, I have to just maintain this order, okay, 2, 1, 3, 6, 5, 7. So basically, you can say 2, after that, maybe 6, 5, 7, and then maybe 1, 3. Okay, this is one of the possible way, okay, or maybe you can say 4, and then I can insert 6, then maybe 2, then maybe 1, then maybe 5, then maybe 3, then maybe 7. This is another possible way. Okay, there are many other possible ways. Okay, even you can exchange 1 and 3 like this, even you can exchange 5 and 7 like this, right? So basically, there are total 80 possible ways. Okay. So this is little trickier question than the earlier one. Earlier one was also trickier. Okay, this was also trickier, that what is the total number of possible ways to get the height 6, or another was to get, the skewed tree or zigzag tree. But this is possible. This is basically they are asking to get the balanced binary search tree, or to get the perfect tree. Okay, how many possible ways are there? 80 possible ways are there. Okay, so you observe one thing is that getting this is more probable. Okay, getting this is more probable than getting the skewed tree. Okay, so getting a skewed tree is basically just 64 ways, like you can insert in 64 ways. So getting a skewed tree is just 64 ways, and here you are having 80 ways. So this is more probable. Okay, okay, now let's just see the next question, what they are saying. Let T be the binary search tree with 15 nodes the minimum and maximum possible height of TR. So you can basically see this. That's very easy. A single node has 0 generally. So basically, the maximum height could be 14. I mean, with two node you get one height. So maximum height could be 14. Okay, so 14, and minimum height will be actually 3. I mean, for the 15 nodes, you can get till like this, right? So basically, minimum height will be 3 and 14. So B is the answer. Okay. Let's see this question. The pre-order traversal of binary search tree is given by this. Then the post-order traversal of this tree is. Okay. So the pre-order traversal is given by this, and the post-order traversal they're asking. So again, in order is sorted. Okay. So you can basically check this in pre-order. This is left, right, and sorry, root left, right. So root is basically 12. So 12 has to be at the end. In the post-order, it is at the end. Okay. So 12 has to be at the end. So anyway, you can basically first make the tree. Okay, you have to first make the tree, and then you can find out the post order also. Okay, great. This question has been asked very recently in 2020. In a balanced binary search tree, the n elements are there. What is the worst case crime complexity of reporting all the elements in this range? Assuming there are k numbers in this range. Can you tell me? We have already solved these kind of things. Okay, this is from the topic which is called range search in binary search tree. Right? Range search in binary search tree, which is order of m plus h, right? M is the number of nodes, okay, in the range, or maybe here they are given k, so k plus h, okay. So k is the number of nodes in the range, and h is the height. So k anyway you will be visiting, h is the height. Why? Because at every level you will be getting at most two nodes which will be pushing you, okay. So here since it is balanced, it is log n, so order of n, order of log n plus k. Okay, that's easy. Sort of log n plus k. You can easily solve this question. Now let's see. The pre-order traversal of this is given. Which of the is post-order traversal? You actually have to make the tree and then you can do it. Okay. Great. Yeah, that's interesting. They're saying a binary search tree contains n distinct elements. What is the time complexity of picking an element that is smaller than the maximum element? Okay. See, they are saying smaller than the maximum element. They are not saying is second smallest. Okay, just see here. They are not asking for the second smallest. So they are not asking for second smallest. Right? They are not asking for second smallest. So they are just asking for the number which is just smaller than maximum element. So basically, what you can do, you can pick the first two numbers, whichever is smaller. Okay, let's suppose this is 5, this is 10. Okay, maybe the highest is 30 or something. Okay, whichever is smaller. Let's suppose 5 is smaller. You are sure that it is smaller than maximum also, aren't you? If it is smaller than some adjacent number, it must be smaller than the maximum. So you can return this 5. And if this is 5, this is 10, then you can return this 5. So basically what I mean to say, you can pick first two numbers and then you can just return whatever is the smaller is a smaller number. So basically you can say theta of 1. Okay, this is very easy. And Deepak sir has already answered this question. Okay, and he's also saying the same thing, right? In all the standard data structures that we know, if we want to pick that is not maximum, okay, smaller than maximum, the time complexity is theta of 1, because we only need to compare any two elements. Okay, take any two elements that you can access in constant time, compare them and return the smaller of those two elements. Okay, that's great. Okay, actually, I haven't read this note earlier. Now I'm just reading it, and he also talking about the same thing. So he's also saying that we don't need to find the second largest number, or the second smallest or largest. Okay, They're not asking for the, okay, I've written the smallest, but actually it is largest because it's smaller than the maximum number. So they're not actually asking for the second largest number. Okay. So they're not asking for this, right? They're not asking second. We just need any number which is not the largest. So the any two elements and the smaller them is your answer. So order of one is the correct answer here. Suppose a binary search tree with 1,000 distinct elements is also a complete binary tree. Okay. The trees stored, this has been asked very recently. So they are saying that you have 1,000 distinct elements and the trees stored using the array representation of binary heap trees, which means you are storing just like an array, just like binary heap. So basically, how do we store? We store label by label. I mean, this go to the A0, this go to A1, like this. I mean, this is the first element of the array, second element, third element, like this. Okay. If this is the ith position, then this will be 2i position, this will be 2i plus 1. Okay. Like that we store. Assuming that array indices start with 0, the third largest element of the tree is stored at which index? So basically they are saying you have 1,000 distinct elements, right? Okay. If you have 1,000 distinct elements, in that case, what is the index? Okay, you are basically storing those elements just like in an array. Okay. So what is index of third largest? That's what they're asking. So basically, I have already taken one session last year, okay, regarding this question. You can go to this session. So you can just search this, okay, and you can go to this session. So basically, this question I already solved earlier. At that time, okay, at that time there were just 12 upvotes. Now there are 80 upvotes here. Okay, so I've already solved this question last year. I think last year. So basically, what you can do, you can just refer this video. You can just search this title. You can refer this video, and you will be getting the detailed solution. Okay, since it is already there on the YouTube, you can just quickly search this and you can solve this question. Okay, but for now, just sake of completion, I can tell you that what they're asking, and I can quickly solve this also. Okay, but for the if you have any confusion, you can see this video, right? So they are saying there are 1,000 distinct elements and they're asking what is the index of third largest. So let me make one tree here. Okay, so suppose this is the tree with the 1,000 elements. Okay, this is the tree that I have for the 1,000 elements. Now, see, this is, let's suppose, label 0, this is label 1, like this, right? This is label 2, like this. Okay, this is ninth level. So can you tell me how many labels will be there, or how many nodes will be there till this point? Okay, I think the indexing here I'm doing for the label 1. This is, let's suppose, label 1. Okay, and this is the ninth level. So basically, you can say that it will be 2 power 9 minus 1. Or maybe if it is level 0, 0, 2 power 0 plus 2 power 1 till 2 power 8. Yes. So this is level 0, this is level 1. Okay, that's how I'm basically numbering the level. Suppose. Okay. Then how many, if this is level 9, okay, maybe I think I'm doing with the level 1 because then only it will be like this. Actually, it doesn't matter. I just mean to say there is a second last level. Okay. This is second last level or the eighth level. So basically what I mean to say that till this point here, see, if I just go to the solution directly, actually I have only written the solution. Okay. So what I mean to say, okay, this is the first level. They're marking with the first level. Okay. Let's suppose the first level, this is the eighth level, this is the ninth level. Now, if you count all the elements till this point, this will be 2 power 9 minus 1, which is 511 elements. Okay, if you count all the elements till this point, right? Now, if you count all the elements till this point, okay, suppose this label is completely filled, then in that case, it is 2 power 10 minus 1, which is 1023. But I just have 1000 elements, right? I don't have 1023 elements, which means there are 23 elements I don't have. So some portion is empty here. At the last level, some portion is empty. Are you getting my point? Okay. So basically, till this point, I'm having 511, and remaining out of 1000, remaining will be here. I don't have whole. I don't have whole. Okay. This portion is empty, right? So for now, let's understand like this. This is the second last level. Okay. And this is the last level. Till this point, this B, basically you can say this is 511 elements. Remaining elements are there, right? Okay. Now, does this B will be having children? Does this A will be having children? Then answer is no. Okay. See, if I have 1023 elements, complete 1023 elements, then yes, A and B both will be having children. If I have 1022, then B doesn't have. If I have 1021, then I mean B doesn't have right child. If I have 1022, if I have 1021, then B doesn't have both child. If I have 1021, then B doesn't have left child. If I have 1020, then A doesn't have this. If I have 1019, then A doesn't have this. I have just 1000. If I have just 1000, then A and B doesn't have any children. Okay. Since I have just 1000, A and B doesn't have any children. So basically, this is how it will look like. So basically, which means, okay, this is how it will look like. Now, if it is a binary search tree, then I will, and someone asks me that what is the largest, then I will going to write, and I will say, okay, this is the largest, right? If it is binary search tree, then B is the largest. Why? Because A doesn't have anything, B doesn't have any children, so A and B doesn't have any children. So B is the largest if it is binary search tree. What is the second largest? See, in the binary search tree, it looks like this. If this is 3, this is basically lesser than, or maybe let's suppose this is uh, 2, this is lesser than 2, this is greater than 2. So largest is this, right? Second largest is this, isn't it? I mean, second largest is this. So second largest will be here because largest, and it will be smaller than this only, right? Second largest will be here. Okay. So largest will be this, second largest will be this, but they are asking third largest. So what is the third largest? See, if you take the in order projection, right? This is the largest, this is the second largest, third largest will be this. I mean, in an order projection, this is the element which will be coming just before the second largest, right? So third largest will be this. If you take the in order projection, you will get to understand. So basically, this is the second largest, this is the largest, this is the third largest. So they are basically asking you the index of this A, index of this A. Okay, the index of the third largest. So what is that index? So if this index is basically 1, right? Then you can say this index is 3, and this index is, you can keep on going it. So basically 137 and ultimately 255. Okay. So from 1 to 7, and then if you want to find out this index, it will be, I think, 255. And then then 510. So basically, index of this, if you're starting from 1, then index of this will be 255, index of this will be 510. Okay. If you're starting from the index 1, but if you're starting from the index 0, since the indices are starting from 0, it is given in the question, then answer is 509. Okay. So I've written this question, I think after the GATE exam. Okay. Actually, the already detailed video solution is there. If you have any confusion, you can see this. Okay. Now let's see this question, what they're saying. You are given a set of V distinct integers. A binary tree is created by inserting all V one by one, starting with the empty tree. The tree follows the convention at each node. All the values stored in the left subtree of the node are smaller than the value stored in the stored at the node. So it is a general convention that all the tree follows the convention that at each node, all values stored in the left subtree of the node are smaller than value stored at the node. It is a general convention. You are not aware of the sequence in which the values are inserted into T, and you don't have access to the tree. So they are saying that you don't have access to the T, and you don't know the insertion order in which they are inserted. Okay, you just know that there are V distinct integers that got inserted into some binary search tree. Okay. So they are saying that which of the following is true? In order traversal of T can be determined from V? Yes, in order you already know, right? So in order you can know because it is sorted. Root node of T can be determined. You don't know root, you don't know pre-order, you don't know post-order, you don't know anything. You only know in order. Okay. So A is the correct answer. Understood? Let's see this question. Which of the following statement is or are true for any binary search tree having n distinct integer? The maximum length of the path could be n minus 1. Yes, this is true. The in order is always sorted. Yes, this is true. Finding an element takes order of log n in worst case. No. Actually, it could be order of n. Every binary search tree is also min heap. No. Binary search tree and min heap are different. Okay. Min heap says minimum at the top. Okay. Binary and all the elements are greater than this, right? All the elements are greater than this. Binary search tree says that this element will be greater than this element will be lesser than this. This will be greater. Okay. Min heap says that all elements should be lesser. Binary search tree says that this is lesser, but this is greater. Oh, min heap says sorry, the all elements should be greater. Okay. So there's a difference. Understood. So basically, C and D are false, A and B are true. Okay. Now let's just see this question. Suppose the values 10, minus 4, 15, 30, 25, 60, and 19 are inserted in the order into an initially empty binary search tree. T will be the resulting binary search tree. The number of edges in the path from the node containing 19 to the root node of T is. So basically, they are saying you are inserting these nodes. Okay. The number of the T will be the resulting binary search tree. So they're just asking that the number of edges from the root to the 19. So basically, you can just make the tree and you can count the number of edges. So what is the answer? 1, 2, 3, 4. Okay. So 4 is the answer here. You can just make the tree. Is this okay to you? Let's see this question. What they are saying. The numbers 1 to n are inserted in binary search tree in some order. In the resulting tree, the right subtree of the root contains p nodes. So they are saying the right subtree contains p nodes. So it should be p nodes. The first number to be inserted in the tree must be. Okay. So they're asking what should be the first number. See, here, like this number should be such that it should be, you can say, lesser than these p nodes. Basically, p nodes must be here if you have. This should be the number they're asking. And remaining is n minus p minus 1, something like this. So basically, you can say, what should be this number? Can you tell me? Suppose you have, let's suppose n is 10. Okay. If n is 10, let's suppose two numbers are here. So it will be 10 and 9. So 8 will be here, right? So basically, you can directly subtract. Okay. Whatever is the n, you can directly subtract n minus p. So this will be n minus p. Okay. So this will be n minus p. The number will be n minus p. Then only p nodes will be here. Okay. So n minus p is the answer. That's very easy question. N minus p must be the root. So basically they are saying what should be the number. So out of this 1 to n, okay, they are inserting 1 to n. Out of this 1 to n, what should be the number that will be on the root? It will be n minus p. Okay. Let's see this question. Binary search tree contains the numbers when the tree is traversed in the pre-order and the value is printed out. The sequence obtained. So basically they are saying the tree is post-order. So basically they are just asking given the pre-order they are asking post-order. So it is also easy. You can just find out the tree and then you can see the answer. Let's see this. Suppose that we have the numbers between 1 to 100 in a binary search tree and want to search for number 55. Which of the following sequences cannot be the sequence of node examined? So basically you're searching for 55. You just divide into two parts. One is lesser than 55, 10, basically 10, 43. Yeah. So it should be lesser than 45, should be in increasing order, which is in increasing order, and this is in the decreasing order. Yes. So this is possible, right? So A is possible. Similarly, this 90, 68, 62. Yes. This is decreasing. This is increasing. Yes. This is also possible. This is there, this is there, this is there, right? So this is increasing. No, this is not increasing. So C is not possible, right? So see here, this after seeing 47, okay. Now after seeing 47, you will go to right of it. Now every number here should be the greater than 47. Okay. So this is not possible. So that's why C is the answer. Okay. Okay, this question we have already solved, right? We have already solved this question. This was, 7 factorial upon 4 factorial, 3 factorial. It is just asking that how many possible probe sequences are there? How many possible probe sequences are there, right? Okay, so again, this is a similar kind of question. They are saying that, by the way, this question I hope you understood, right? So we have already solved in the beginning of the lecture. So see here, in the beginning of the lecture, we have solved this question. I think, yeah, this is the question, right? So in the beginning also, we have solved this question. Okay. Now let's just move to the next question. So again, this question is also easy. They are saying that 273 has been, they are searching for 273. It could be the successful or unsuccessful, it doesn't matter. Okay. So which of the following is a possible sequence? So you can just divide into two parts and then you can just check. Okay. So option D is answer. Which of the following they are saying in which we could have encountered. So third only. Okay. In third only, they are following lesser than 273 are increasing. Okay, and they are decreasing. Otherwise, I think in all the options, see here, this is 149, this is increasing, but is this decreasing? No, right? After 395, it is not possible to see 463. Okay, everything should be after 395, basically everything should be in lesser than 395. Okay, so 463 is not possible, 402 is not possible, like this, right? So you can solve these questions very easily. Let's see this. A binary search tree store the values in the range this. Consider the following sequence. Which of the following is true? Okay. So they are saying a binary search tree is given to you, and in this range, store the value in the range of this. Consider the following sequence of keys. Which of the following statement is true? So they are saying that first, second, and fourth is possible in order. So basically, you have the values in this range. Okay, then is this the possible in order? See, it has to be sorted, so this cannot be possible in order, so that's why A is not the correct. So for the in order, it has to be sorted. First can be pre-order. Can the first can be pre-order? Actually, we never know. For the pre-order, we never know. Okay, if it is pre-order, then this should be the root. Now they are saying first is pre-order sequence of BST, some BST with 439 is the root. For pre-order, we never know. It could be the pre-order, but 81 must be the root, right? So can this 439 be the root? So that's why this is also wrong. Similarly, for this option D is saying 4 is post order. Maybe it is post order, we never know. But 270 should be the root. But they are saying 149 is root. No, this is not possible. C is saying second is pre-order. Second is pre-order because yes, it is the increasing order. It could be the pre-order where 121 is the root and 52 is the leaf. Okay. See. Uh, See, second is pre-order, definitely. But can you say 121 is the root or 52 is the leaf, something like this? Tell me. This is increasing order that I completely agree. Okay. This is pre-order. See, sorry, this is in order. Now, you can have 121 root, nobody is stopping you. Okay. And then automatically 97 will be there, 52 will be there. Yes, this is possible. You can even have 52 as root. You can have anything as root. Actually, there will be a fixed structure that you can definitely fill, right? 121 and then 195. So like this, you can even have 52 as root. It will be skewed one, right? If you have basically 472 as root, it will be left skewed like that, right? So you can have anything as a root, doesn't matter. Okay. So you can have, we cannot know the root. I mean, there are many possibilities. Anything can be root. Anything can be root. So they are saying 121 is the root and 52 is the loop. Yes, this is possible. I'm not saying using this in order we are able to finalize the root. No, no. But it is possible. It is possible that 121 is the root. Okay. And if 121 is the root, 52 will be the leaf. Yes. So basically, C is answer. Okay, C is possible, right? This is in order, and 121 as a root could be possible. Okay, nobody is stopping. Is this as a root possible? Yes. Okay, so if 195 is a root, then you will be having all the numbers lesser than here, right? No, greater than here, right? So I'm not saying that using the in order you can find out the root, but yes, the possibility could be anything, right? 121 is the root, and in that case, 52 is a leaf. So basically, this answer is not little bit more detailed. Here you can add a line, okay, that anything could be the root. The possibility, if you just ask me the possibility, yes, 121 could be the root. And in that case, 52 is a leaf. How many different binary search trees are possible with three distinct keys? As you know, there are five structures, right? For three keys, we have the five structures. Okay. And each structure you will filling in exactly one way. So B is the answer. These are the five structures. Okay. So that is all I wanted to discuss, right? So we have completed all gate PYQs. Right? I think this topic is easy, not that tough. So we have completed all gate PYQs. Now we will be going to the gate PYQs of stack and queues. Okay. So now next lecture. Okay, great. So I think today we are already at the 3 hours, so we can have this lecture tomorrow. I thought actually today we might be able to solve all the questions just 2 hours. Okay, so maybe we can have this tomorrow. Okay, I will schedule it and we will be having it tomorrow. Okay, thank you everyone.